Там очень надо.
Може мікрофон поставити вниз?
Це я за мікрофони не відповідаю.
Лише зараз пишете чи ні?
А?
Як у вас зараз?
Ні, я пишу з загального фону, з камери. Тому що вчора, по-перше, мікрофоном не користувались майже.
Ні, цим користувалися.
Ну, там лектори ж бігли вправо, вліво, вони ж без мікрофону були.
Оце не силовий, він абсолютно не потрібен, слова ніхто не вищає.
Було б зручно, якби були, знаєте, такі телебачення.
Вчора про них поговорили, що типу
Вони є, але, на жаль, підключити зараз їх до цього ноутбуку, так як вчорашній на нього сів якийсь вірус, не є можливим.
Щоб якщо лектор буде тут стояти, щоб щось було?
Ні, його чутно буде, все чутно.
А може краще туди назад поставити, якщо він буде в екран дивитись?
Якщо він буде знову дивитись в екран, то тоді краще поставити зразу сюди.
Так, трансляція вже йде.
Так?
Так.
Якщо в нього діаграма напрямленості дуже така вузенька.
У ці сферичні. Цих сферична діаграма.
Просто на вигляд це шотган. Так називають.
Але це сферичні.
Олексій Михайлович, трансляція є, скопіюйте просто цю ссылку собі на сайті, все, я покажу.
Так воно вам не заважає? Дивіться, будь ласка, в камеру.
Ну, ось ссылка на сайті, ось.
Ссылка есть, да?
Да.
Сейчас делаю.
Все, я скопіював.
Сейчас быстренько отправлю.
В камеру гляньте, будь ласка, вам в цьому місці мікрофон не заважає?
Не. Посмотри на картинку.
Нормально все. Все нормально. Сейчас.
Ты дальше не снят ничего. В прошлый раз.
Це і вимкнений пульт?
Увімкнений.
Телефон камеру не опускать.
Кристина, пока.
Пока.
Так. Сохрани. Копировать. Английский.
Якщо немає цього кадра, що зали. Я ще раз покажу.
А кто тоді брав ключ від деканата?
Я не слышу.
А, ты? Я думал, что тут есть.
Сюда перенеси. Отсюда будет не совсем удобно.
Добрий ранку. У нас є проблема.
Какая?
Професор, меня зовут Макинтош. Я забыл адаптер для видео.
Адаптер для видео.
Или... Это маленькая штука.
Я знаю, по-моему, что это надо менять.
Да? Я думаю, что может
просто в любой другой компьютер взять.
Проблема в том, что есть видео, и я могу это готовить.
As our director.
Yeah.
Good morning. Nice to meet you.
Сейчас рисую.
How are you?
Fine. The problem with Macintosh, so I forgot the video adapter. And the question is whether someone has.
Is it
Я
possible
думаю, що
just
краще
to,
всього, щоб скинути флешки на інший
to
комп'ютер.
connect flash?
А ми зараз питаємо,
Then,
може у когось є. Я теж
Then I
просто-
need to reformat this. So
Так, а ну зараз
focus on
зробимо.
videos. I can do it, but it's not going to be optimal.
У нас адаптера нет, если перенести в другой
We
компьютер.
don't use Mac in our process. We are using Microsoft
Yes.
notebooks.
В документі
Mostly. So,
в документі нема помарочки.
Okay, then I will
А
transform
треба
to.
подивитися.
it's, maybe this is
Там є
not optimal, but
там є
maybe
десь
it's
в тому. Чуєш, Леша, а там же є той?
Понимаешь, его надо как-то поставить, чтобы мы могли...
Чи там є короче, подписати? Таку ну... Есть? Вы не знаете? Это мьют или это? Так. Он не горит пока. Не горит?
Да не включается, а выебок нужно.
Интересно. А. Не загорелся? Чтобы все кнопки он не нажал.
А какой-то нет, конечно.
Кто-то видел.
Надо было...
Обещал, что будет.
Пока был Василий, надо было его спросить.
Ну, я его спрашивал, он просто хотел убежать.
Ну да, не мог и помочь.
Интересно, далеко ушел? Сомнительно.
А сейчас это будет это самое главное местного, потому что
Интересно, он лучше знает, что пофиг.
он обещал быть, но я не знаю, если он решил, что у нас опять вечером, например, сюда придет через часу.
Особо далеко не
Интересно.
Там далеко не ожидал.
Ну тогда больше нормально.
Один человек находится, другой за камерой сидит,
Да. Мы сейчас будем смотреть, как это будет. Сами. Да, шикарно. Что?
Камера закрыта,
Да, ну, один идет прямой эфир.
ты думаешь,
Питання, немає комп'ютера. Главное, декорации не сильно. Я думаю, что тебе об этом интернет тоже, да? Ну, точно будет.
А вчора ми працювали у вас, ніхто не включав.
Никто не включит. 16 теж можемо послухати.
Ні, ну тут було, тут якась одна штучка, яку треба просто...
Ці комп'ютери всі стоять, їх ніхто не чіпав. Це, напевно, мілки.
Так, попробуем. Смотрите, там все.
О,
Это
поговорите.
все выключайте, вот кнопка, которая включает.
Раз. Это самое, уровень.
А теперь регулируйте. Нет, вот здесь...
Чуть-чуть нижче.
Микрофон, да?
Раз. Леша, а ти дзвонив тому Лімітову або куди йому можу позвонити? Галі позвонити. Є у когось в залі ноутбук? Є? Можете його позичити для доброго діла? У нас нема коннектора до макбука і треба перекинути просто. Презентацію.
Залить куда-то и скачать обратно.
А куда? Компьютер никто не взял. Ты же не взял, я не взял. Флешка есть.
Простите, пожалуйста, у вас должна быть чувствительность и громкость. Чтобы не фонить, чувствительность сделайте меньше, громкость больше. Я с этим не работаю.
А я думаю, это работало.
Просто либо микрофон уберите от прямого излучения диффузора чуть-чуть подальше в глубину сцены. Тогда не будет шуметь.
Просто вот эти кнопки.
Подальше.
Не, все нормально. И там буду чуть, и тут буду чуть. Не нормально, не зашкалює. Раз. По-моєму, вони дуже тихо зараз.
Тихо?
Да, нормально.
Если не подойдет микрофон, а вот эти две кнопки. Вот эти говорит, что... Да, это регулировка. И вот.
А это что?
А кто отключил?
Это уже на миксере все. Вот это под микрофон, а то общий, нет?
Да. Я сейчас его буду, наверное, набирать.
Потому что он обещал быть, я не знаю.
А вот это что?
Потому что если камера здесь стоит, то если мы будем водить за человеком, то либо мне его надо ставить определенные рамки.
Что такое отставание?
Что-что? Это здесь оно так тормозится, что тут нормально есть. Вчерашнюю запись уже.
Нет, я имею в виду там.
Но это нормально.
На сцене.
А что с сценой нормально?
Микрофон.
По микрофону сцену тут говорить надо еще. Вчера без микрофонов работал. Поэтому, ну, так. Да, я все хорошо снял, просто мы выходили туда прямо зеленым на переднюю планку, и камера приходила все чуть-чуть ближе. Ну, и вы можете посмотреть. Я сейчас выйду на сцену. А вот посмотрите вот сюда.
Я не могу на одном месте стоять. Я
Нет,
должен ходить.
Вы все время вот там стояли.
Не прятаться за цветочек, я понял. Держаться ближе к центру, хорошо.
И потом тоже, я все время волновался, вы очень близко к краю подходите.
Не, я не падаю, это сам, падать я не падаю.
Получается окончательная точка, то есть вы на передний план вы выпадаете.
Я понял.
То есть это вот на этом промежутке можно спокойно...
Знаете, как у собачек делают невидимый ошейник? Надевают, и она не может выбежать. Хорошо.
Разряды мы не будем посылать.
Сигналы.
Тогда оно просто сейчас идеально стоит.
Доброе утро.
Доброе утро. И в наборе кабелей.
Это вы с нами связаны?
Так он USB HDMI, да? USB или HDMI. Сейчас.
Нет.
Хорошо, тогда до четверга я в среду постараюсь приехать, в четверг чтобы как бы подтвердить, я приеду. Да, хорошо. Спасибо.
Сейчас смотришь кадр, и мне покажешь точку, где вот стань здесь, вот смотри, стань здесь и смотри. Где я буду выпадать по тому краю.
Да. Нет.
Вот здесь точка.
Ну, это крайняя, самая крайняя точка.
Чем нам ее повесить?
Да, вот у меня есть предложение. Какой-то маленький кусочек бумаги. Вообще было бы идеально, если можно было эти вазоны двигать. Как-то вот так на край. Кусочек просто сюда.
Пускай ставят на это место.
Подождите, сейчас проверим вот этот ноут. Здесь должен быть нормальная видеокарта.
Да, надо выключить, пока мы самое тут он плавает. Он сейчас выключит. Он сейчас выключит. Да, то есть щелкните. Слышит вообще.
Все нормально. Не прям только компьютер брали. Ага. Что? Кто такой? Сейчас я подойду с этой стороны.
Ольга, you still need my computer?
Прошу вибачення, ми маємо поки що деякі технічні проблемки, які з'являються. Немає коннектора з MacBook, тому перекидаємо на інший комп'ютер.
Проблема з софтом. Війна Apple та Macintosh. Сьогоднішня Apple та Microsoft між собою і месенджер.
No, that's Now we're connecting it to projector or connect this camera. At the back, I guess.
For the camera. Yeah. No. Okay, I remember that.
When it is here, you try remote, it works, and you try to stay in this area, then you will be filmed. Yeah. Wait, but why it's not your slide? I made a slideshow.
Slideshow.
Yes, let's make a slideshow.
And then I need to. Somebody needs to tell me how to use физики. So
No, it's
So this goes, look at the screen. Just press the arrows.
okay.
Back
There's only
forth.
two options.
Only two options, right?
Super.
Super.
Simple.
It's simple. It's one.
If you press something else, it will go red. And then if it goes red, it will not do what you want. So then just call me.
So
press this and that.
only these two buttons.
Just two buttons. That's it. Nothing else. Nothing. It's one-dimensional system. Even it's discrete. It's it's not.
Welcome. I'm sorry for short inconvenience. We had some technical problems, so now hopefully all is resolved. And I'm pleased to announce our first speaker today, Ulf Leonhard from Weizmann Institute, who was one of the first people who started to pursue the topic of invisibility quarks. If you know what is that, it's connected to metamaterials. And he is studying actually optics of nanostructured media, optics of metamaterials, and the first talk is about the art of invisibility.
Yeah, thank you very much for the introduction. Thank you very much for your patience. We had to sort out some computer problems before I could start. So I'm talking about the science of invisibility in this lecture. And what is invisibility? So first, it's a subject that comes from this part of the world. So it's a subject of illusions and deceptions and things you see in a strange environment, like in the desert over there. And it's an optical illusion like a mirage. So sometimes when you are out in the desert, you see that you see mirror images. So you see a reflection of the sky in the air, and that is an optical illusion. It's a mirage. And now this illusion happens because the hot air above the sand is able to bend light. So it's bending light that comes from the sky, and then it's reflected and reaches your eye. And this is the reason for all optical illusion. It's simply bending of light, that light doesn't go along a straight path. The simplest example is the one you see here on the screen, and that is if you look into water, then for example at the fish in the water, then you see the fish at a different position than where it actually is. The reason for that is that light rays that come from the objects, that carry the image of the objects, they are not traveling along a straight path. They are refracted at the interface between water and air. And you, on the other hand, you assume that the light rays that strike your eyes, that they always propagate along a straight path, and therefore, for you, the fish is at a different position than where it actually is. So that is an example of an optical illusion, and it's caused by the bending of light. Here it's the most extreme example, so it's refraction, so it's a sudden change of direction. But you can imagine if you have a material where the optical properties, the refractive index varies gradually, then this refraction goes also in a gradual way, and so light is then gradually bent around an object. So therefore you see things differently. So optical media, optical materials change the perception of space. Now, the ultimate illusion is perhaps to make things completely invisible. So here at the mirage, you see that there's something going on. So this is an unnatural phenomenon. You see that you see objects where they don't belong, but invisibility is to make things completely disappear. So that's perhaps what constitutes the ultimate optical illusion. Now, the science of invisibility is fairly recent. So these are the first papers related to this subject, and if you look, what is interesting about them, so they appear roughly at the same time. So this was the earliest is 2003, and then you see there's one precursor in 2005, then there are two papers in 2006. So around that time, the first scientific publications on invisibility appeared, and It took also some effort to actually publish in this field because there was nothing there before. Everything before the literature, before that, was really, if the clicker works, so was this. Literature, films, myths. This is what existed before that time. And you can classify the literature in this field before and after, roughly according to two different subjects. One is the invisible man and the other one is the invisible woman. So the invisible man is a figure from a novel by Herbert Wells, and in this novel he's a chemist who invents a substance that changes his refractive index. What he does, he makes his body transparent by giving it the same refractive index as its environment. Light does not care about what the particular material is, it only cares about the refractive index. So if you happen to have the same refractive index as your environment, then to light you are the same as your environment, so light just goes through you and therefore you disappear from view. It makes you completely transparent. This is not a good idea because you need to change yourself in order to make this happen. And also, if you read the novel, it doesn't end well for the lead character of that novel either. Now, the second possibility of invisibility is personified by the invisible woman. What she does in the Fantastic Four, so cartoon and also film, she has some sort of force field from outer space with which she can bend space. And in doing so, she can send light around her, and then this light doesn't touch her, and therefore she becomes invisible. And if you send light around in the proper way so that it moves in the same direction where it came from, then you wouldn't be able to see that something has happened. And so this is a way of making herself invisible. And this, as it turns out, is a more practical way than invisibility, than the method by the invisible man, although in the scientific literature there are also proposals related to the invisible and sophisticated ways of making things invisible that are similar to that. Now, I started investigating this problem around 2002 and thinking about what you can do with a dielectric material where you change the refractive index gradually. As I said, there the light rays can be bent in a gradual fashion. So the idea was simply that suppose you have some material and then light rays from the distance, they are gradually bent by the material and in such a way that when they leave, they go in the same direction as where they came from. And they go around an interior region in the middle that is not touched by light, and therefore it becomes completely invisible. Moreover, because they leave the device in the same direction they came from, you would not notice that something has happened to these light rays, and therefore for you this would be nothing had happened, so that you wouldn't see that anything was not to be seen there. And so this is invisibility. The problem is, so the advantage of dielectric materials is that you can in principle do this. So the invisible woman from the Fantastic Four, she has some sort of force field. You don't need that. So you can achieve the same effect with materials, dielectric materials that have a designed refractive index. The problem is, how do you find the right distribution of refractive indexes? So how do you design this? It's not a problem if you want to make something invisible from one direction. That's easy to design. You can do it in this way, or you can also use some mirrors and things. People have done this. The problem is, how do you design invisibility from a range of directions or from all directions? And the inspiration to this problem comes from a different area of physics. It comes from the physics of space and astrophysics, general relativity. And it comes from a connection between geometries and materials. So in general relativity, you also have this phenomenon of light bending. In fact, it was one of the early tests of relativity observed by Eddington. That is, that the image of stars appeared to have changed during the solar eclipse. The point was that the sun was deflecting or was bending the light rays coming from the distant stars, and therefore, in that projection, they appear to have moved slightly outward. Now, you can do exactly the same with a refractive index distribution. So you can just easily, actually, in fact, design a material that has the same effect as the gravitational field of a star like the sun. So in general, there is a connection between materials and geometries, and in its best form it's expressed as it's shown here, as a connection between Einstein and Maxwell. The connection is this, so that Maxwell's equations, as you know them, they are valid arbitrary geometries and in arbitrary coordinates. If the only thing you have to change are the constitutive equations. By Maxwell's equations, I mean the equations that contain all the four fields. So they contain the electric field E, the magnetic induction D, B, the displacement D, and the magnetic field strength H. And what the geometry does, it changes the constitutive equation. So it changes the connection between the dielectric displacement and the electric field, or the magnetic field induction and magnetic field strength. So this is where the geometry appears. Now you can turn this the other way around. You can say, if I want to create some geometry that corresponds, for example, to the deflection of starlight in the previous pictures, then what I need to do is I take the expressions that come from geometry and I implement them with dielectric materials. So I take an epsilon and a mu with exactly the properties that I need in order to make this happen. So that's the way how you can design geometries using dielectrics. And I want to show you one example of unusual physical or optical phenomena you can get with it, not invisibility yet, but on the way to invisibility. So this is the example essentially with which I started from. So you look into water, into a fish, or let's assume that you have some point particle in the water, and that is sending out light in all directions. That's shown here, red lights, they are the light rays going out of the water. And then what happens is they're refracted at the interface between water and air. Some are totally internally reflected, so the angle is shallow enough to the surface. Others, they can get out of it, but you see that they're going in a range of directions and with a range of refraction angles when you leave them. So this means, oops, this is too fast. This means if you look, that is, if you trace back where these rays come from, so if you assume that you're seeing in straight lines, then you see that the image of this point varies. It varies with the angle in which you look at it. That's something you can easily observe. If you look into an aquarium, then typically what you see is that the object inside, like fish in an aquarium, they appear at a different position than where they actually are, but also this position changes. If you move around, you see it again at a different position, and so on and so forth. So that means that the optical illusion created by the material is easily called off as an illusion, because this cannot really happen in reality. So you see that something fishy is going on here. Now, let's take this example. So this is essentially almost the same thing, except that this is a material where the refractive index varies radially, and therefore the light rays are also bent in a radial fashion. They originate from one point in this example as well. Now, let's take the same exercise. So you trace back all these light rays, and now you see miraculously that they meet at one point. That means if you have a material like this, then the image of your object is always at the same position, regardless from where you look. So this is really a perfect illusion, so that the picture does not change does not depend on the point of view, and hence you would not be able to tell easily whether this is an illusion or whether this is reality. Now let's go one step further. So what you can do is this. So you see that you can discriminate between two spaces. So one is physical reality. So this is what light rays really do, so they are band. And the other one is the space that you actually see. So let's call this virtual optical space. And this space is created by tracing back all the light rays to the point from which they appear to have originated. Now, because it's really one point is mapped into one point, you can dispense of the procedure. So it's not important how these points are obtained. What is important is that there's one point in physical space that has a well-defined image point in virtual space. And you can do this with all points. So what you can is that this material performs a transformation of space, a coordinate transformation of space. This is an idea that is very much perpetuated in general relativity. So coordinate transformation, that is the method to create unusual optical illusions. And this is what I proposed in 2006. So that a coordinate transformation as the basic tool for making things invisible. In that case, it is actually a special coordinate transformation. It's a conformal transformation that does not change the angle between your coordinate lines, and it has the advantage that it can be implemented with an isotropic refractive index distribution, and so that therefore it's close to what people normally can manufacture in the laboratory, or even what natural materials have. The problem with this is that you need some extra tricks. So you can show that with only conformal transformation, invisibility is impossible, and you need to do some further manipulations that are required in order to make things disappear. Therefore, it took me some time to figure this out. Now, there is another method that's conceptually much simpler, where you only do a coordinate transformation, but then it is an anisotropic material that is required, because as you see from this picture, the angles between the coordinate lines are no longer preserved. So we have physical space, we have virtual space, and there the coordinate lines are there under different angles. Now, this is it's the conceptual simplest because of the following reason. So that this is how here in that case invisibility works. So you have in real space, we have objects like these fish shown over there, and in virtual space, this is the space of the optical illusion. What happens is that you take the interior of the blue area in the picture, so including the blue fish, and you project it into a single point in virtual space. This means essentially you demagnify objects, so you make them appear to be of infinitely small size. If the size is infinitely small, it's invisible, and therefore everything inside of the blue region has become invisible. And you can do this in a finite region of space. So this finite region is indicated by the light blue circle in the picture. This gives you the dimensions of your device. And then the blue circle is the inner dimension of the device. So this is a cloaking device, a thick shell that transforms space around it. And so it's a map of real space to virtual space. Virtual space is the space you see, and therefore in this space you have just one point representing the object, and that point is visible, so therefore it makes things disappear. Objects in the shell themselves are slightly distorted. You see that the shape of the fish is slightly changed in that shell as well, but outside of it, nothing, of course, would be changed. Now, you can ask, how does that correspond to the picture of the bending of light rays? And it's very easy to answer. You see this in these diagrams. The left diagram, as usual, shows virtual space, the right real space. And you see that a light ray is a straight line in virtual space. You can put it on one of the coordinate lines. Now, in real space, because you perform a coordinate transformation, this coordinate line is no longer a straight line. It's distorted, it goes around the object, and so therefore you see that this picture of sending light around objects is naturally implemented with coordinate transformations. Now, the procedure is then this, so you write down what the corresponding negative tensor of the coordinate transformation is. You put this into this equation, you get epsilon, you get a mu, and then this in principle gives you the recipe of making an invisibility device. The problem is, how do you do this in practice? So if you want to impress your friends at the patent office, in the old days you had to go to the patent office, then what do you do? And the problem is, because for those transformations of space you need extreme properties of materials, and there one of the possibilities is to use what is known as structured composite materials or metamaterials. And here's an example of an invisibility device. It's an invisibility device for microwaves. It's very hard to do this in optics. I will show you an example of what can actually be done in optics. For microwaves, it's easier. And one of the reasons is because you can engineer materials much easier for microwaves than you can do in optics. And you create structured materials. This is a very, very simple recipe here. It's made of circuit boards. So you take a typical circuit board, this is plastic with copper layer on it, and you etch structures in it, and these are these split ring resonators that are etched in the copper. Now, to an electrical engineer, they would look like electrical resonators, simply because what you see it looks like a capacitor. That's what you have in the middle. Then you have some bands, they act as inductors, so you have a combination of capacitance and inductance that gives you resonance. And if you change the capacitance, you change the resonance frequencies, and so therefore you can tune the response of that resonator very easily simply by giving it different shapes. And that's what was done in this particular experiment, where the conductance was changed from one layer to another in such a way that it corresponds to the bending of microwaves around object. Now, this is something one can do with microwaves. In optics, this is very, very hard. What is done in most experiments in optics is not full invisibility, but something rather like this. So it's optical flattening. So what you can do is you can make a round object to appear flat, like in physical space you have another fissure, fugu, and you can make it appear as flat as a flat fish by a transformation. And this is a transformation that is easier to implement in practice. It doesn't require extreme properties of the material anymore. Moreover, it can also be done with isotropic materials. That's shown in the example down there. So you can, in principle, do this with a conformal transformation or quasi-conformal transformation. And therefore, this is something that is close to practice, and therefore most of the experiments are of this type. So I want to show you one of those experiments. This is a lab in Birmingham where these two gentlemen will show you how to make things invisible. What they make invisible is a paper clip. So it also shows you how modest the attempts are in invisibility, at least for the visible magnetic spectrum. So this is an object to be made invisible, or to be precise, to be made completely flat. So you see two prisms here. So the transparent prism in front of it, this is calcite. It's a birefringent material, and it's cut in a precise way required for the transformation that is performed. Then the golden prism in the back, simply there, the front end is the only decisive part. It acts as a mirror. So this is a diagram what is happening. So you have a mirror, then a paper clip in front of this mirror, and then this calcite cloak or calcite structure, if you like, in front of everything. What they're going to show is how this looks like in images. So they take a panda and then look at this panda, so they look at the light that comes from the panda, and then they have to use a polarizer because the calcite is birefringent, so it depends on the polarization, what refractive index you have. It will only work for one of the polarizations. And so if you put the polarizer right, then you should see the paper clip appear completely flat, so it's part of the mirror, so you shouldn't see it anymore. However, if you use the wrong polarization, then you will, of course, see a distortion caused over the image shadow of the paper clip. So this is what you see. So this is the look now from the polarizer. You see the panda on the side, and then again this is how it looks. So this is the wrong polarization there, and then if you put the polarizer right, you see that the image of the panda appears. So the paperclip has been transformed, has been made as part of the mirror. So this is what you can achieve in practice now. So you can make objects appear flat of a size of a few centimeters. What limits this is simply it's the crystals you can get. So they got some very good crystals from China to make this happen. If you would have larger crystals, you can do it. That's what people have achieved so far in terms of optical invisibility for microscopic objects. Now I want slightly to change gears. So I want to show you that this idea of invisibility by transforming space or transforming space in general has wider applications. I was very pleased to see this, so how that field has caught on and how it made it into different areas of physics. So one other application is thermal cloaking. So you may need it at these temperatures, but this is not what the picture actually shows. It's this. So it's a cloaking device that cloaks thermal conductivity. So this is the experiment in STEM. So it's very simple. So you have hot water and cold water, and you look at the conduction, at the heat conduction through a copper lead between the hot and the cold part. And the goal is to make essentially that you could put something inside of it, make it disappear according to heat conduction. So this is not thermal cloaking in a sense that you protect yourself from cold in that case, or that you're losing heat to the environment. And this is not thermal insulation, it's thermal cloaking. So, and it really is based on the analogy between optics and thermodynamics. So what you see in optics is have propagation of wave, and thermodynamics we have heat transport, and heat transport is a diffusive process. So it's not exactly the same as in optics. There's no wave phenomenon associated with that. Now, if you have insulation in optics, so in optics you could also make yourself very easily visible simply by screening yourself. So you put something around yourself, you would not be visible, but of course everyone would see that there's something to be seen there. And so if you do it like this, so you enclose some metal, for example, around an object, desirable object, a bit of money, for example, then you get reflections all over the place. And in thermodynamics, so thermal insulation is the same. So you insulate an object, and then you will see that the conduction of heat is of course changed by the thermal insulation. Now the point of thermal cloaking is to avoid that, so that the heat conduction really goes on as if there were standard uniform material. You would not be able to see that the flow of heat is altered. So that's what they have shown in the experiments, so these are experimental data. Another example that is also related to diffusion. So suppose this is your bathroom, and you live on the first floor, and naturally you would like to protect your bathroom against burglary. So what you do is you put some bars in your bathroom window to the outside wall. This doesn't really look nice, does it? So it makes you feel like you're in a prison. So it might be desirable to get rid of those bars, at least in its image. So the question is, can you remove those bars from the picture? And yes, you can, and you can do this in a similar way as the modification of the conduction of heat. And in fact, this is relatively easy to implement in practice. So what you do have here is also a diffusive process. So in the bathroom window, light does not simply go through, but light is diffused. So it's scattered many, many times in the internal structure. So there are some droplets or some colloidal structure inside, and so light is reflected many times and is diffused through the structure. And what they have done is they have designed, with just a few layers, a material that is able to then send diffused light around the object. So this is how it looks like in reality. And these pictures, they make a comparison. So you have, as you see here, there's some aquarium that's filled with a water paint solution in the experiment. You can also leave the aquarium empty. And so the left picture shows that you just have an empty aquarium. The right picture, you have water paint solution in the aquarium. So the first one is there's nothing there, so you see that no object. Then you put the rod inside, and then you see in the air, of course, the shadow of that rod. But also in the water paint solution, you see that there something was there. That's what you have seen in the bathroom windows. Now, if you put then this cloaking structure around this, and just a few layers, I don't remember exactly what materials they were using, it was something very simple. And so if you put this around, then in air, it will just make your object appear slightly thicker because you have some more structure on it. But in the water paint solution, you clearly see that the object or its image has disappeared. So you can make your bathroom windows look decent. You may say, well, this is just a gadget, so this is not a real problem. The real issue is there are situations in technology where this is important, and that's, for example, in solar technology. So if you have a solar panel, then in order to get the produced electricity from it, you need to put some wires on the solar panel. So each solar cell produces a certain voltage, and you want to add up all those voltages, and you want to then lead the current out of it. And this needs to be done with wires, and these wires have a shadow. If you are able to reduce the shadow of the wires, you can increase the efficiency of a solar cell by a few percent. You may say, is that important, a few percent? Yes, it is. So every percent counts in this business, and therefore this is really an important improvement of what solar cells can do. Another example. So we talked about diffusion instead of wave propagation. Let's go to a different part of the world, and that is the sea. So what kind of problems do we encounter in the sea? And the problem in the sea is that it looks like this. So if you're down there, then this is what you see. Therefore, animals who live in the sea, they don't use sight for orientation or finding their prey. They use sound. And the most impressive one are the sperm whales. So they have in their head they produce directional sound, and they then can also record. They can hear the echo from the sound waves, and in this way they can find their way in the deep ocean. They can find their prey in the deep ocean, so they can live there. There are other creatures as well that use sound. These sort of technological things that are also relying on sonar to find their way, and also they try to avoid detection using sonar. So therefore, this is a natural issue to look into the propagation of sound. And here is an example. This is the first experiment that was published in this field of the modification of sound waves using a cloaking structure. You see, this is a very small structure, nowhere comparable to the size of the submarine. And they put this into a small container with water, some object inside, so a star that would scatter sound waves, and then if you take the image using a hydrophone, you see the shadow of the sort of sound waves. On the other hand, if you put this metal structure around the star-shaped object, then you see that the sound waves are nearly perfectly preserved, and hence the hydrophone will not see a difference. So therefore, if you have some object that you want to hide from sound waves, you could do something similar to this. You can cloak it with an appropriate acoustical structure, and then it becomes invisible to sound, inaudible to sound waves. Well, why stop at sound? There are other waves in nature, and the most impressive one are the waves from earthquakes. So this is earthquake is nothing, just a wave, and the most destructive waves of earthquakes are actually waves that run on the surface of the earth. The trouble with earthquakes is that that's what they do. So they have quite a large intensity, and they can destroy things. So you may wonder, it might be desirable if your house is in an area that is prone to earthquakes, that you want to protect it against those waves. So when the earthquakes come, you want to send off the earthquake in a different direction, preferably to the house of your neighbor, for example. And can you do this in principle? And as weird as it sounds, so there are experiments that try to show that this is possible in principle. Here is one, and they did this in a parking lot in the French Alps. And they did this as follows. So what this experiment should show is the deflection of waves comparable with the waves of earthquakes. And it's not the cloaking of waves so that they go around an object and don't touch it and propagate as if they started before. It's simply a reflection of those waves. And for this, they drilled holes in the ground. These holes, they create a disruptive interference of those waves, and so therefore they can say, in fact, they act as a mirror for waves comparable with earthquakes. And so this is what you would like to put in front of your house. And there's certain holes drilled into the ground. And then the layer behind this, these are holes that contain seismometers. So they want to detect what actually goes through. So they put their instruments everywhere. And then the digger you see in front, this was the digger used to drill the holes. But it's also the digger that makes the waves. So they use it to create the waves, 50 hertz. And they record what goes there. They could in fact prove that it's possible to manipulate those waves. The next part of the experiment that they really want to use explosives. So they want to create a strong wave and then see whether such waves are actually reflected or possible to reflect such waves from there. And you can do other things as well. So you can go into acoustics and do it also for nice acoustical manipulations of pleasant sound waves that you would like to hear. Right, so this is some examples from the science of invisibility. What drives and also what limits this field is essentially it's the ability to imagine. So what you can do with unusual connections between different areas of physics, following very much the same of Einstein, that imagination is more important than knowledge, because knowledge is always limited. Whereas with imagination, you can embrace the entire world with all the everyone which know it and understand. And with this, I would like to end, in particular with the transformation of the two heroes of the story, Einstein and Maxwell, into each other, which is also an example of a coordinate transformation. Thank you very much.
So, can we move to the first slide, please?
To the first slide.
Yes.
Okay, so let's see whether the computer can do
It's invisible man and invisible woman.
Okay.
Yes. Yes. I don't know about invisible woman. Maybe she manipulates space in some other kind. But invisible man for sure is blind because he doesn't perceive any photons of light which pass through him.
Okay.
And the invisible woman may bend all the photons around her, so she's is in the dark too.
You are raising an interesting question. May I send this question to the audience? So the question is, suppose you're wearing some invisibility device, so some layer that sends light around you. Would you be able to see something? So who thinks that you would be blind? Okay.
I think there are ways around it.
Why?
I think there are ways around it. You don't have to be blind.
You can see something.
Yeah, I think you can.
Is there anybody else who thinks that one can see something? Not really. So let's go to the sides of it. So that is this picture here. So what does the cloaking device do? So it makes yourself appear to somebody else the size of a single point, right? That's what it does. So the question is rather, can a single point see something? What do you think?
It can't, because the flux of light from outside will be near to zero, because the intensity stays the same, but the surface area is much smaller.
But take a single atom. So a single atom is very much like a single point, and you can see single atoms. You see them if they're written.
Yes, but they see with some quantum flux. They have very big noise in them.
I disagree. So you could. It's true. So when you come to atoms, then quantum mechanics is important. And so the details of how atoms perceive light are, of course, they're governed by quantum mechanics, but not the principal mechanism. So you could also imagine a classical near point-like antenna, and that would act like an atom, and it would be able to perceive the electromagnetic field as the atom does. However, what the atom cannot see, it cannot see images, right? It cannot see from which direction the light comes from. For this, you need two eyes, so two atoms, and then you will be able to do that as well.
Also, as promptly shown on this picture, while one fish is hidden, the other fish is distorted. So invisibility clock of this sort is not really fully invisibility clock.
No.
Because
it's not true. So the other fish is simply it's one that is in the shell of the device. Of course, you don't want to have any fish there, so it should be transparent, completely transparent. This is simply to indicate that there you do a transformation. So if you happen to have something there, then of course it's going to be distorted.
yes.
So in reality, and reality means, like in the experiment, these calcite crystals, they should be as perfect as possible, as transparent as possible. You have nothing there, and therefore you don't see that they actually inside of themselves distort space.
Also, another large problem for invisibility clocks of this nature is chromatism, because each different wavelengths of light will be different, differently in real materials.
This is a big, very big. This is actually the decisive problem for full invisibility, and which makes it impossible really to appear in practice. Now let me. The video doesn't start, so let me try to just be a little bit patient. I want to show you the last picture of the video. So there you see exactly what you said. So the chromatism. So this is now the shadow of the paperclip disappears. You see a few fringes. It's visible light, and it's a relatively broad band of the spectrum. You see some artifacts. So you saw that it's not entirely perfect, and there are some artifacts due to there. But in principle, for transformations that appear to flatten objects, this is not as crucial. So you can do that in principle over some range of the spectrum, and therefore get a reasonable approximation to an optical illusion.
So, for example, if you take the shortwave one, is it really applicable to real-life situations? For example, can we clock real-life plane visit? Because real-life radars, they can tune the frequency in some very narrow range. Can we cover all of this narrow range with a single sheet of material?
So one thing, so the perfect cloak is to make a plane appear like a single point. This you can only do for discrete set of frequencies, or for one frequency, and strictly speaking. What else you can do, so how well you can approximate the things, I have no idea and I don't want to know. So this is not the field of research I'm going to enter.
So,
discussion. Questions. So,
How large objects can be hidden nowadays? During the nowadays technology.
what do you mean by hidden? So for electromagnetic waves, light, or acoustic object. Sorry, for
Visible light.
visible light. I think what I showed you is the largest that people have achieved in the flattened picture. There are other ways. You can, if you know that you're looking in one direction, then you can. There are nice videos on the internet actually, so that you can make people disappear. So it's the size of people, but you have to know that you're looking at some person, like in the end of the corridor, actually looking only in one direction. Then you can make the person completely disappear using these kind of techniques. And you can do this with mirrors. So a simple arrangement of mirrors is enough to achieve that effect in one direction. There, of course, there are other ways of making things invisible. So the simplest is you record an image with a camera and you project that image onto the person. These sorts of things have been done as well, and then it's person size, what you can achieve, or even larger. I think there are plans in South Korea to make a skyscraper visible by recording the image from the other side and then using LEDs to project it on one side of the skyscraper. Whether that is a good idea, I doubt very much, because you want to make a skyscraper visible, particularly if it's close to an airport. But that's what I read. There are plans there.
Yeah. So about the bathroom,
Yes?
if I want to make my bars invisible from the inside, maybe it's a good idea to keep them still visible from the outside, because otherwise they won't work.
Right. Yes.
Can one do that?
Well, they would work, but they wouldn't deter the thieves.
Yeah,
so.
you'll have to replace your window.
This is a tricky question. So the question is, can you? So it's about reciprocity. So yes, typically, so in like electromagnetism or optics, materials are reciprocal in the sense that when they go from A to B, they can also go from B to A along the same path. There are materials where that's not the case. So where the objects on the way back, or the let's say light on the way back, can move on different paths. I'm not sure whether this is possible for diffusion. So can you have diffusion in? I'm not sure.
No way. I mean, it's Laplace equation and it has a symmetry which is arcus, you know.
Yeah, of course. But if you don't have Laplace diffusion, so you may have like diffusion in some anisotropic material or some. So I'm not sure. So this is it's an interesting question. Whether diffusion can critically be made known as
maybe using polarization, making it one polarization.
Exactly. By using some Faraday insulator.
Yeah, then it will only work for the burglar with polarized.
Actually, that might help already. If the burglar has the appropriate sunglasses, then
yeah,
you would deter it.
Well, you can only outcoming light from your bathroom make polarized. That's what you do in your bathroom your way, right? So you can make all your light polarized.
Yes.
So what comes out is polarized.
Yes.
That you can.
To watch.
Can those invisible objects emit radio waves, and how they behave?
So again, so in principle, yes. So you have, because what you do is you shrink them to the size of a point. Question is, can the point send out wave? Yes, it does. So the atom sends out light. So in principle, you can do that. So you can also use them as sensors, so for detecting light, and you can also use them as emitters. Actually, what I want to say, the point of sensors is that you can use if you use some cloaking structure around the sensor, you can limit the footprint of the sensor. So all sensors need to, because they extract energy, they're distorting the electromagnetic field. But the question is how much? So how can you minimize the distortion created by a sensor? And with these cloaked structures, you can do that. So you can have sensors that distort the field as little as possible. And then on the illumination, you could also think about whether these tricks of using materials to modify the structures of space, whether you can you can modify the illumination patterns. You do, in fact, you actually do that. So not with these techniques, but there are sophisticated ways of lightening. So these are so-called freeform lenses. So where you use very strange shapes of directed objects in order to have maximal efficiency of lighting. So you get an LED, which is good approximation for a point source, and you want to make it turn it into a wide beam and in a short as possible space. So for a car light, for example. And people are working on this, and the most recent applications of this are video goggles that they're weird. So like for virtual reality, where you're putting goggles on yourself and then a computer projects the image onto you. And then also the problem is how do you reduce the size of those goggles? And you can do this with freeform lenses. So with very smartly engineered electric distribution, you can reduce the path needed from point source or near point sources to a wide beam in order to reduce the size of those goggles and so on.
The last question. Yeah, can I ask one more? Sure. Yeah. So your original recipe for making things invisible by conformal transformation that creates a horizon, boundary between visible and invisible, always seemed to me reminiscent of black holes, where you have a horizon beyond which you can't see. And of course, we can see a black hole from the outside, so it's not part of that story. But is there other effects like at the black hole horizon? In this case, do you get some entanglement between inside and outside? Because
so
the inside is invisible.
Just a comment on the black hole. This is also related to your previous question. So the black hole is non-reciprocal. So because you can fall inside, but you cannot get out. And I have another lecture, then later in the afternoon you will see why. Mm-hmm. So why black holes are non-reciprocal. So why there are traps. Why you can get in, you cannot get out. However, so these spatial coordinate transformations, they are reciprocal. So if you can get close to the closed structure, then you can also go back. And the only thing is that there's some region in space that is excluded from. And now this is because it's simply a passive transformation of space. So all you do is you have some dielectric material. There's no reason why you get some entanglement like by light production. So they will not produce, these structures will not be able to produce light themselves. They can only transform it, and they should in fact transform it in such a way that you don't see. So that I don't think that there are sources of entanglement as they are. So we need to modify them in a way that we can do that.
Yeah, but if we wanted to use optics to mimic entanglement in black holes, can we do it using some reciprocal Faraday effect?
I have a lecture this afternoon about exactly this.
Yeah. Okay.
Okay.
Move to the next lecture. Let's thank the speaker again. Next speaker is Leonid Levitov.
Should I leave this?
Yeah, we need to. Самое главное вот эти джазы. розеток. Есть одна, есть еще, даже две есть еще. Нормально. Я сейчас исчезну на часок. Потом уже заказал. На углу. Ну, на 6 до 6. Ну, так, более жду, более просто. Ну, я, если надо, я.
Change of title, as I see. So the next topic is something about physics and
good morning. Let's let's see where we are. So maybe let me apologize for changing title. I mean, it was partly intentional because I didn't know what comes. I just gave tentative title that would be then refined to anything. Changed because yesterday some people came after and said what exactly are you working on now? I mean, don't tell us about what you worked on in the last millennium, but tell us about what you work on right now. And so that's partly the reason. Also, just looking at listening to questions, I thought maybe this will be more appropriate than what I thought about initially. Also, can I ask just two questions, just to calibrate myself against the audience? How many people here are undergraduates versus graduates? Okay, and undergraduates, right? And then how many people here came today but didn't come yesterday? Because then maybe I should repeat what I said yesterday at the end for those people. Because so yesterday there was somehow a discussion at the end about education issues and something like that, and maybe it caused some questions, and people came and asked, and so maybe we should do it again today. We'll see. So great. Okay, good. So let's start with graphene. Graphene is a big subject, and because there will be one more talk about graphene, I will have to do a little bit of introduction, also to explain you what graphene is about. I apologize for this color that wasn't supposed to do. I got some computer glitch. I projected, which I'm not sure it looks perfect there. So graphene now is, it grew into a big field studying 2D materials, which are two-dimensional. And so there is a large family of 2D materials which can be isolated, down to a single atomic layer or two atomic layers like graphene, and its relative or nitride that look like a chicken wire, two-dimensional atomically thin chicken wire layer, and then there are various other atomically thin materials of different kinds. They can have different electronic properties. They can be conductors or insulators, or nitrides, wide gap insulator. These materials can be medium gap, can be semiconductors, medium gap, narrow gap. There are superconducting materials with charge density wave, and then logical materials. So there are materials of all different electronic properties. All can be made one layer thin. And so there is a big field of studying these materials. A reason people are interested is that these materials have some interesting properties that listed here. They're thin, transparent, flexible, optical active. They have a wide broadband absorption. They have states which are exposed. You can act on them by proximal gates and change their properties, their permeability. And so these material properties, they manifest themselves in a variety of physical properties, and so there is a wide range of people who are either exploiting these properties to build some useful devices, or trying to use the physical effects that follow from these properties to do some interesting physics. So there are at least two directions: trying to do some physics and then trying to build devices. And maybe just to as a quick introduction, something from maybe the mother of all these two-dimensional materials, graphene, is a carbon monolayer with this structure, and from a crystallography point of view, it has a two-atom unit cell, because two carbon atoms that are marked red and blue, they are not equivalent under translations. They are equivalent under translations combined with conjugated degree rotation, and because of that, the band structure has two branches, and because of that symmetry, rotation, and translation, these two branches have connection which is protected. They touch, and this connection cannot be the points where they touch cannot be easily removed by any perturbation that agrees with the symmetry. And this is a result of low energy band structure near these points where the two bands touch, being of this form. If you zoom in and linearize, so that then we get near these points we get behavior similar to massless Dirac fermions, where fermion wave function is two components corresponding to wave function amplitudes on the blue side and the red side, and the Hamiltonian that describes it is a 2x2 matrix Hamiltonian, where two spin components correspond. They're not spin; they're pseudospin in the literature, and they correspond to wave function amplitudes on the two sides. So it's an interesting material where the spatial wave function mimics spin in the Dirac equation, and this is more or less an exact mapping. One can use this transformation to write down Hamiltonian for low energy states that will look like massless Dirac Hamiltonian with a two-component spinner in the literature, called Survival spinner, and one can add electromagnetic fields and in the canonical way, long derivative to couple to magnetic field, and adding scalar electrical potential, and so this model will describe everything that happens in the graphene with conduction electrons near the Dirac wave. And in this approximation, there is no coupling between Dirac fermions here and Dirac fermions here, where they're independent species, and some coupling appears at high orders perturbation, but zero approximation is just two decoupled valley species that each of them behave like massless Dirac particles. Okay, so yeah, I realize that probably this is too fast for some people, and also useless for other people because they know all about it. So please, stop me and ask questions when you want to clarify something, because then otherwise we'll lose people too early. We don't want to lose anyone to grow. We want to lose everyone eventually. Yeah. So graphene is the mother of two-dimensional materials, of course, and of course we've got two mothers, or maybe better to say fathers, which are pictured here, and to whom owe the excitement of studying graphene. So with that, we see. Yeah. So the Maslow's-Dirac Hamiltonian defines, graphene as a model relativistic quantum mechanics system, and one can, see that there are very specific properties that are derived from Maslow's relativistic character of electrons in graphene. In particular, this linear dispersion relation that we saw over here near the Dirac points, as they're called. It makes electron dispersion, energy versus momentum, very steep, and that allows electron properties to be gate tunable over a very wide range, because energy versus momentum varies very steeply. You can vary carrier density by applying a gate potential in the range of a few volts. So that's much higher than in any other known material. Usually gate voltage variation is at least 10 times smaller than a typical semiconductor. So there's a wide gate voltage range that's useful, and that wide gate voltage range translates into a wide range in which you can vary the chemical potential. So you can vary the Fermi energy in graphene. You can vary the Fermi energy in graphene by tuning voltage on gate on the gate over a range of a volt, and that's unprecedented because all other semiconductors have a number which is much lower, and it makes graphene very interesting from the point of view of optics, because you can vary it over. You can vary your Fermi energy over the energy of which is the energy of a photon, and you can block or allow optical transitions by acting with voltage on the gate. So that's something which is widely explored now in building devices. And likewise, another property which is derived from a relativistic Hamiltonian is the chirality. The fact that, as you can see by staring at this Hamiltonian, spin orientation is locked to velocity, and because of that, carriers propagating one way have their spin, zero spin, aligned along the velocity. So that has implications for scattering. Suppressive back scattering makes material immune to disorder, and ultimately that explains why electronic properties are so much better than one would expect in an atomically thin material, which is exposed to all kind of environmental conditions, disorder, etc. And so high mobility of graphene is in fact due to that chirality effect, which is relativistic in its origin. Right? And so these two effects, they are well understood and they're widely explored in devices. There are various devices, maybe we'll leave it for questions, that rely on what I just said. But then there are also other properties which are also relativistic in their origin, haven't yet found their way into engineering. In particular, there is interesting effects due to Berry phase in these materials, and so that's what we'll talk about today. Also, if you think about electron-electron interactions, graphene is an example of a model system. You have quantum electrodynamics type of phenomena at strong coupling, and so that leads to many interesting physical effects, and is under intense investigation by physicists, and not yet by practical people. Right. So yeah. So I think, yeah. Sorry for this blue background. So Right. So what I would like to do today is to focus on the Valley degree of freedom and how we create topological currents in the Valley degree of freedom that transmit transmit Valley variable and we'll be using in particular the fact that electronic states in graphene are exposed, and so you can put in something nearby and alter electronic structure to make it suitable for Valley transport. So we'll focus on that small subspace, and that with that I proceed to my main part of the talk. Maybe I should stop and ask if there are questions about general things.
What's topological current?
Huh?
What's topological current?
Right, that will come. Yeah.
What's with spin?
The ordinary spin. The regular spin. So
yes.
The regular spin is always there. Atom. It has small atomic. It is not coupled to Dirac spin because spin orbit is very small. Carbon is a light atom. It has small atomic weight. Because of that, spin orbit in this atom is very small. Also, when you make the spin structure, every atom has a very symmetric environment. That suppresses spin orbit coupling even further. So spin orbit coupling in the band structure, graphene band structure, is very small. So the real spin is just nearly completely decoupled from orbital motion, and it makes it kind of boring from some point of view. But also there are people who like it because if you want to observe long spin lifetime, then graphene is a good material. You can inject spin and see that spin polarized electrons can diffuse around long distances without spin flipping. And so some people like graphene because of that, to realize long range spin transfer. But that's precisely because spin doesn't show up in Hamiltonian. Yeah?
You're talking about electron spin or nuclear spin?
Electric or what?
Electron spin or nuclear spin?
Oh, electron, yeah. Nuclear, right, there is carbon 13 and carbon 12, right? So one has nuclear spin and one doesn't. There is in principle possibility to make graphene with, in which every atom has nuclear spin. I don't know if people looked into it yet. Maybe not. I mean, it's interesting, but I mean, people have done some of that with carbon nanotubes. There are carbon nanotubes where all carbons are spinful, and then they have some interesting properties. But I don't know if anyone did it with graphene yet. But anyway, so the question was about electron spin, and we're not going to. Even electron spin is not important. Yeah. Yeah.
This is super spin velocity locking effect on scattering. I actually didn't know about it, and the question, will it be the same as the logical electron?
Yeah.
I mean,
exactly.
It's not distinguishable.
So it's distinguishable in the sense that here there are two valleys, and everything will be identical to topological insulator as long as there is no inter-valley scattering. But if there is a valley scattering, then it will become a different story. I mean, usually it's a weak effect, but present to some extent, and so it may make a difference.
Yes. My question is the following. This expression for the Hamiltonian, can that be derived analytically?
Yes.
Through formulas from first principle Hamiltonian?
Yeah, yes.
Or
So
this
this
is just a parameterized description of the numerical solution for band structure?
Well, you can do both. So you can do ab initio calculation and compute all bands in graphene, and then see that near. Yeah, I mean, we should have this discussion in principle, but it will eat up into the rest of the talk. But I mean, you can do a full analysis starting with carbon 4 electrons in the outer shell, and then how they hybridize with each other, and then, as you know, it forms an sp2 configuration with 3 electron orbitals hybridizing with 3 carbon neighbors, and sitting in plane, and then the 4th orbital sticking out and forming an H-shaped orbital perpendicular to carbon plane. So the configuration is not like a diamond sp3, but like it's a lower symmetry sp2. And then if you start with that as an approximation, then you can show that first 3 electrons are too far from the Fermi level. Their orbitals basically don't matter. So the one that matters is H-shaped one, and then one can do more analysis on this H-shaped orbital and show that they after you treat them, they lead to this precisely this band structure, and it will be half field. So the Fermi level, just from counting number of electrons, will be sitting exactly in the middle. So in pristine graphene, which is undoped, the Fermi level will be right here. So we'll have all Dirac antiparticle states filled and particle states empty. So that follows from either kind of analysis, ab initio or that chemistry type, and one can do it. It will take one time. Yeah, sorry.
Yes. So this equation, Hamiltonian, has one constant. The speed, if I recall correctly, is growth speed. What order of magnitude is it for real material?
This one?
Yes.
Yes. So it's 10 to the. Oh, sorry. Yeah. So I have it. So it's about speed of light divided by 300. So it's 10 to the 6 meters per second, which is typical for any solid. Another way to remember it is E squared divided by H. Electron charge divided by Planck's constant is 10 to the 6 meters per second, close to that. And it's velocity unit typical for solid. Yeah. Okay, so let's move on. Right. So what we want to do is exploit the fact that graphene got several valleys and use that to study transport phenomena where we create currents that flow in the opposite direction. Currents for species in each valley that flow in opposite direction, one valley relative to the other valley. These currents will not transmit charge; they will only transmit valley index, and they will tend to lead to valley imbalances. Takes carries in one valley flow right, carries in the other valley flow left. There's no net charge flowing through space, and so these currents, because they're charge neutral, they're interesting. They can be long range because they don't lead to any charge buildup or electric field buildup, and but they carry something. They're carrying some degree of freedom, and so in principle can be used to encode information, and there are many proposals of that. And so in graphene there are specific tricks that one use relying on Berry phase to realize valley currents, and so this shows basically the idea. If you think about graphene band, you realize that you can equip graphene band fairly easily with Berry's curvature, and we'll see what's that in a moment. And if you have Berry's curvature, Berry's phase and Berry's curvature, then there is an interesting change of equations of motion of particles. There is an additional term. But if you forget about this additional term, what you see here is the ordinary group velocity equation, saying that velocity is just the group velocity of carriers derived from their energy versus momentum relation. So that's what we always write. And then for momentum, so that's for position times derivative. And for momentum times derivative, we write the usual Lorentz force equation. But turns out that with Berry's curvature, this system is incomplete, and you get additional term which looks like Lorentz force term, but it's in momentum space, not in position space. And in the sense, after you add it, the pair of equations becomes more symmetric. The equation for position times velocity in position space and velocity in momentum space become, look very much.
What physically is omega? What this omega is physically?
It's Berry's curvature. It's a flux. It's a flux of Berry's field. But just wait. Yeah, no, we'll talk about that. But if we manage to achieve that, then what we can do is to have something like a Hall effect, but without external magnetic field, which will be controlled by Berry's curvature. And Berry's curvature is nice because it will be tunable by gates, because you can move your Fermi level up and down, and peak large Berry curvature, not so large Berry curvature, and use that. And also another reason that's nice is that unlike Hall effect, which is of the same sign in both valleys, this one will be of the opposite sign in both valleys, because Berry's curvature will be of the opposite sign in the valleys. And so using that, we'll be able to realize these valley currents that we wanted, where current in one valley, current in the other valley flow in the opposite direction, and you get a charge neutral valley current. So then we begin to answer Grisha's question so let's recall the Berry's phase fields. I mean, I don't know how many people saw it in quantum mechanics class. It is usually part of it, but maybe not. Well, just in case. So Berry's phase appears as part of the discussion in the diabatic theorem. So diabatic theorem, derived in 1928 by Born and Fox, says that quantum mechanical system, which also in time, tracks an instantaneous eigenstate of the Hamiltonian if the Hamiltonian is changing in time slowly enough. And this is correct, but as Berry shown in 1982, 83, is incomplete. And in fact, there is also a phase effect that is due to this time variation, and it turns out that in this time evolution, the state tracks instantaneous eigenstate, but picks up additional phase that depends on the path the system is taking in configuration space, and can be expressed through something that looks like Aronoff-Bohm phase, but generalized to be not in position space, but in any configuration space. So at this point, K just labels phase space in which parameterizes the function. Whatever parameter you vary will be called K, and then if your instantaneous eigenstate varies as a function of K, please take derivative and then take the inner product with an eigenstate, and that gives you the Berry's vector potential. And then if you integrate it over a path in configuration space, that gives you Berry's phase. And I mean, it's a fundamental part of quantum mechanics in general, and the diabatic theorem in particular. It's interesting. It's an interesting phase because it's geometric. It doesn't depend on how fast or how slow you move. It only depends on the configuration of your path in the phase space, and it's independent of change of phase of the wave function. So if you worry about gauge invariance, it's gauge invariant. So it's it basically has all the properties as the Aronoff-Bohm phase. And generalizes it to an arbitrary quantum evolution, right? So that's a one-page summary of Berry's phase. Maybe let me ask a question at this point. How many people have seen this? No? Okay, shall we derive it? No?
Yes.
Okay.
Let me explain.
Does anyone even care? No.
They are here, they do care.
You care? Okay. Okay, so let's take 1 minute. We have some slides that maybe I can use to put a figure on that. Yeah, so please ask questions, because otherwise, I mean, I don't know where we are on this. So if we want to, if we want to prove a diabetic theorem, let's start slowly. What do? We take a time-dependent Hamiltonian, and then for every instant of time, we take a basis of eigenstates. These eigenstates, because the Hamiltonian changes in time, they also change in time. So it will be a rotating basis in the Hilbert space. And we can look for a solution to Schrödinger equation, which is a linear superposition of these instantaneous eigenstates. And then the phase in that evolution, we can first write down naively. We can say that at each instant of time, we have a spectrum of the Hamiltonian given by a set of energies En. And what we can do is we can write the phase factors which are simply integrals of instantaneous energies over time, which if energies are constant will be a linear time phase factor. If they're not constant, we have to write down an integral over time En of t dt, right? And one can do analysis in this instantaneous basis, which is orthonormal at every instant of time, and prove that theorem, right? So this is how it's done. So like we said, we'll seek solution in this form. Each instantaneous eigenstate multiplied by the phase factor, which is energy integrated over time, and then we'll put in some time varying coefficients, and then we'll put it into the time-dependent Schrödinger equation and derive an evolution equation for time varying coefficients. So we first plug it in, then we use orthonormality to project on the nth eigenstate, on the mth eigenstate, and m and n states are orthogonal. They satisfy orthogonality relations. So here, from the left-hand side, we only pick up the term number m, and in the right-hand side we have the whole sum. But in the sum, we have one term where these phase factors, which in general vary rapidly because evolution is slow, and so the time over which energy is integrated is long, and so it gives big phase factors. So the big phase factors, if they cancel, we get a slowly varying term. If they don't cancel, we get a rapidly varying term. So we want to make this distinction and separate the right-hand side with slowly varying term and rapidly varying term, and then argue that all the rapidly varying terms don't matter, right? So because they oscillate too quickly, and if we integrate, it will make a much smaller effect than this term. So if we argue that and drop them, then because of fast oscillations, then we'll have a simple first-order differential equation with c dot m equal to cm times some number, and then using orthonormality, you can show that this number is in fact pure imaginary. It's a very simple exercise, and so that means that this first-order time evolution generates a phase factor, which is this thing integrated over time. Okay, done. Questions? Yeah.
What is En of dt prime? What does it mean?
Right. So the intuition is that before our Hamiltonian was time varying, when Hamiltonian was constant, this was the phase factor with which each eigenstate varied in time, right? You have constant energy, and then each eigenstate will have the phase winding at the rate proportional to its energy. And now energy is varied in time, so you have to basically, generalize its phase winding, but make the rate of phase winding, which is the energy, change in time. So that's what this expression is. At every instant of time between 0 and t, this phase is winding at the rate given by the instantaneous energy.
But D is T prime.
T prime is the time over the time on the interval between 0 and the final time.
The energy of T prime, not the argument is wrong.
Oh yeah, of course not. Yeah, forget all that. Yeah,
D is
yeah. It's
why is purely imaginary? There's a simple argument why it's purely imaginary. It's
yes.
unitarity.
Yeah, just read this. I mean, you're quick. You can do it. Yeah, that's an analysis. And basically, because if you have a state that changes in time, the velocity in Hilbert space, the change of the state in time is always orthogonal to the state. As a result, if you take inner product, there will be no real part in it, only negative. Yeah, more questions? I mean, let's settle. Yeah.
This division on slow and fast oscillating terms, why it is eligible? What is it?
So it's only good when we are, considered a diabatic variation. It's a good question. I have to be more careful here. So this is only good if we consider a diabatic variation, and what it means is that the rate which my Hamiltonian varies is smaller than the scale I get from energy level spacing. So I'm looking at the state number n, it got state n plus 1 and minus 1 above it and below it, and the energy splitting must be large enough compared to h bar over characteristic variation time. I mean, otherwise we cannot discard these rapidly varying terms because they will vary at the same rate with which our Hamiltonians vary, and there are no separate time scales. All right? Yeah, someone. Last call.
Okay. Cool.
Okay. Right. So actually, so there are similarities between all phase and various phase that are interesting and will be discussed. And some people will believe their own of all phase when it was introduced, and it was the same as various phase. But I mean, this is all now settled. Let's not. I mean, it's So how do I start view? Okay. Right. So okay. So we are. So now we have our Berry space, and I mean the main point. I mean this duration is not so important after all. The main point is that Berry space is very much like electromagnetic vector potential. It generates a phase for whatever configuration space your system varies in, and it's a non-trivial phase if your system makes a loop. So it's very much like a loop effect when you have a magnetic flux and the particle goes around it, and it can go around it, stay all the time in the region of physical space where there is no magnetic field, there is only vector potential, and the curl is zero. Nevertheless, it will pick up the phase vector, and it will lead to observable effects in the absolute vector. So the same here. The main phase effect is due to loop integral of vector potential, and you can express it, of course, by Stokes' theorem through flux of a curl of vector potential through an area with a boundary on your loop, and so you can write this as an integral, as an area integral of this omega area being this one, ordered by the loop, and the loop will be in whatever configuration space you are using. In our case, it will be phase space, momentum space, but in other examples it can be something else. And so this curl is in fact called Berry's curvature. So it's like magnetic field, but for Berry's vector plane. And it will not live in the real space, it will live in whatever configuration space Berry's curvature handles. Right. So there is an example of spin 1/2 particle that may be, again, it's something which is part of a standard quantum mechanics course, but just in case, let me say that if you take a system, a simple system where this can be explored, is a spin 1/2 magnetic field, and the Hamiltonian is Zeeman Hamiltonian with spin. So this is now real spin 1/2 particle. Coupled to magnetic field, then if your magnetic field is constant, spin will precess about magnetic field. If magnetic field is time varying, it will precess about time varying magnetic field. But if time variation is slow, it will keep precessing about time varying magnetic field and track it, right? And so that's the classical picture that we can derive from classical beam and torque equation. It's an agreement with the diabatic theorem. And what Berry's phase adds to it is that in this time evolution, there will be an additional phase contribution that will be proportional to the Berry's flux through a loop and configuration space. So in this case, the configuration space is the two-dimensional sphere because our magnetic field can point anywhere in space, and one can do simple analysis and show that there is a simple geometric interpretation of Berry's curvature in this case. It will be simply proportional to the solid angle subtended by the loop. So if I take my magnetic field varying in space, the solid angle which will give Berry's curvature will be the solid angle that I see. If I do it very quickly, then there will be a loop, and this loop will define some solid angle, and Berry's curvature will be exactly 1/2 of that solid angle. And what one can show that the general definition from previous page translates into this geometric solid angle formula. And it's very easy to derive. It's actually the next page of those slides. If anyone is interested, let's discuss at the end. But the reason I'm saying it is that if we now apply it to graphene electrons, which is described by this massless particle Hamiltonian, then this looks like Zeeman Hamiltonian for pseudospin, of course, not for real spin, which is coupled to some effective magnetic field proportional to aligned with particle momentum. And so if I make momentum vary, if I like to go around in momentum space, then there will be a phase that I will pick up, and this phase will be calculated by the solid angle. And in this case, actually, things are a bit special because my system is two-dimensional, and because of that, my momentum is always in plane, and because it's always in plane, the solid angle that I showed will be a 2π solid angle, because my momentum, if I go around the Dirac point in some way, my momentum will go around equator plane, and so the solid angle formula will predict 2π solid angle divided by 2 will give pi Berry space for Dirac electron, and so that's the that's all of it. right? So so one can apply the concept of Berry space to transport of electrons in crystals, and do it carefully for Bloch states, and just using momentum of Bloch states as a parameter, and this leads to many interesting things. Your Bloch bands acquire Bloch of Berry space and Berry's curvature, and that leads to logically non-trivial effects. They acquire what people call topological Sherman variance, which integrals the Berry's curvature of a topological band, and that leads to a whole field of geometry-inspired physics. So I'm not going to do any of that. I just mentioned because it's something that is very active now and constantly being discussed. Maybe the last thing, which is in part of a general type of introduction. So let's suppose we have that Berry's H field, and we want to derive equations of motion that I postulated with that additional Lorentz-like term. So how do we do that? There are many ways, but perhaps the simplest one is to do the following. We can write down an effective action for positive particle motion, just using the canonical procedure. Take P and X phase space, and then write down the action, which is P times velocity in position space minus the Hamiltonian as a function of P and X are treated as independent variables in phase space. And then to that add terms due to vector potential. So this is the ordinary one due to electromagnetic vector potential, electromagnetic times vector potential times velocity in position space. And if you do that and forget about Berry's part, and then look at the Hamiltonian equation of motion derived from Hamiltonian principle, then you get Lorentz force equations, and it's very easy to generalize to Berry space, because Berry space is the same thing as electromagnetic Aron-Bone phase, but in momentum space. So all you need to do is just to put two vector potentials, one that lives in position space, one that lives in momentum space, and gives an effect proportional to A times velocity in momentum space. And if you take that and then put it, still put it in the Lagrange equation of motion, or through the Hamiltonian principle, then you have to do a bit of algebra here, but at the end, your equations are just what we said. So if you use this term only, you will get a Lorentz force equation. If you use both of them, you will get Lorentz force in position space, and then Berry's Lorentz term in momentum space. Done. Yeah.
We have a typo there because Lorentz force is why is a term with EA times P dot? Why it isn't simply P?
Because we are, okay, so let's go maybe a bit back to where we said. So it's this, right? So I have to integrate A in a product with displacement in momentum space, but I can write displacement with momentum space as velocity times dt. So then dk will be k dot times dt, and so that's what we did. Yeah,
so we get an acceleration in Newtonian.
No acceleration, no, it's just velocity. Well, it's velocity multiplied by time difference. So it's really displacement, infinitesimal displacement. But it's written in this, it's written in this way just to make it look canonical. This is a canonical action. Action written as a time integral or Lagrangian, or Lagrangian is what we see in parentheses. So that's a Lagrangian in phase space. And if you take our expression for Berry space and put it through this, write down displacement, infinitesimal displacement as velocity in momentum space times dt, then you do exactly the same thing for electromagnetic part. question? No?
Yes, you do, but such things are, in my opinion, better described on a blackboard, and it's hard to follow from slides.
No, I agree, but I mean, what, you know. Yeah. Anyway, so I cheated. I must tell you that I cheated a bit here, because when you derive these equations of motion, you derive them for canonical P and canonical X, and to go to physical P and physical X, you have to use long derivative condition and shift P to P prime minus A and X to X prime minus A Berry, but that's standard. So you have to do a bit of algebra in between, and at the end you get the right equations. I mean, Lorentz equation is very important to understand various ways, and to try deriving it like this, and even if you don't care about various phases, try doing Lorentz equation. It's a lot of fun. Yeah. So we do care about this term. So it's this term that we're going to use now to realize Rayleigh transport, and I only got a few minutes left. So the effect from this term I can understand intuitively as a kind of curveball effect. So when you play tennis, if you spin the ball, it will skew sideways, and that's a general feature of motion of any object that carries vorticity. So you can think about various curvature as vorticity, which is being carried by electron in a solid. And if you are in addition to its charge, velocity, position, there is also vorticity degree of freedom that various curvature describe, and it allows you to do just this, make the ball skew sideways, baseball in this case. And I mentioned this classical analogy because it's true for any object carrying vorticity, and it arises, in this case, it arises from Magnus effect. In our case, it arises from various physics, but anyway. So this contribution to current, is what's called topological current. Someone asked earlier, but so now we have current or velocity, which has a normal part, which is group velocity, and then also this topological part. So the topological part is what we're going to use, and I mean there is a big field exploring it and using it to study topological effects. Now we are only going here to look at the Rayleigh currents, the Rayleigh Hall effect, and the task is to convert graphene, which, as we mentioned before, it has Berry space, but doesn't have Berry's curvature, because Berry space is always pi, no matter what loop you calculated on. So our next question is how to convert graphene into a topological material where you have Berry's curvature. And for that, I think I'm really out of time now. So for that, what we need to do is open up a gap in graphene band structure. And if you open up a gap, and the way to do it is to find a perturbation that produces asymmetry between red side and blue side in graphene that I showed earlier, and this will lead to Dirac mass appearing in graphene spectrum. And as soon as you get a Dirac mass, you get a pocket of Berry's curvature, positive for one band, negative for the other band, near the Dirac point. And one can do calculation and show that in this case solid angle, you get a non-trivial solid angle that will vary as the size of the loop in K-space, so you get a well-defined Berry's curvature. And so the question is, can you do it with graphene and play the curveball? And so this is unfortunately the part which is central for my story. I only got 1 minute for it. So let me show you collaborators and the final result, basically. So these are students at MIT and experimentalists in Manchester, and collaborator from Exeter University sitting there. And so what you can do several ways, but the way that we implemented was to put graphene on boron nitride, and boron nitride turns out to be nearly lattice matched with graphene, so it creates creates a perturbation which distinguishes between red sites and blue sites, and in this way opens up a band gap. This band gap, Dirac mass gap, has been measured, and it turns out to be quite sizable. People see it from activation behavior and transport near the Dirac point, and from activation behavior they infer this value, which turns out to be, real value turns out to be a bit higher, closer to 500 Kelvin. It's now confirmed by optical experiments. So it's a narrow band. I mean, in this, when paired with boron nitride, it becomes a narrow band semiconductor with a fairly sizable, gap that allows to do interesting physics, and in particular create Berry's curvature and explore its effects. Then it turns out that there is an interesting dependence on Berry's curvature distribution on whether graphene and boron nitride is axis aligned or axis misaligned. There are different kinds of structures, and they lead to, if you do analysis, it will lead to different kinds of distribution of Berry's curvature in momentum space. But in both cases, you get a pocket of Berry's curvature at the Dirac point. In one case, it's positive, in the other it's negative. But you can use it for what we just said, for producing this topological current term in equations of motion, and then inducing value currents and controlling them. So people, we're not the first ones doing it, controlling values. It's been done recently using optics. We are doing it using transport, and so let's not discuss optics. So in transport, we want to avoid these equations of motion to produce currents which run in opposite directions in different values, like we said before, and we want to detect them. So how do we detect them? The way you detect them is, so here, I forgot to say that current that you induce will be transverse to electric field if you apply. So it will really look like Hall effect, which is what we expect from a curve, right? It skews sideways. So if you apply a normal electric field, this current will go in the transverse direction. And to detect that, what you do is that you take a long system, a long strip, and take a pair of contacts here, apply ordinary electric current over here. This ordinary electric current will create a charge-neutral valley current along the strip, and then this charge-neutral valley current, because it does not produce any field buildup that is when the current gates along, it can flow as far as intervalley relaxation allows it, which in practice means up to 10 microns. It's really far. And so at this remote location, you can put in another pair of contacts, and then there, by a reciprocal of that valley Hall effect, you will get an ordinary electric voltage. So the detection scheme is that you use one pair of contacts to excite it, and then here charge-neutral currents will propagate, and you measure a non-local voltage signal far away. And it's a little bit like, a loose analogy with radio, where you have one charge circuit that excites charge-neutral information carriers, i.e. photons, and then on the other end they are detected by charge circuit again. Right? So finally, the experiment. In experiment, there is a long graphene strip with several pairs of contacts, also graphene attached to it, and you can use one of them to apply current and the another pair to detect voltage. And then there is also a backgate by which you can vary chemical potential, Fermi energy through the entire band, and you see spikes in non-local signal. So the red curve is a non-local signal, and this alignment with local transmit measurements indicates that the non-local signal happens exactly when your Fermi energy goes in the region of K-space where you have Berry's pocket. The pocket of Berry's curvature, right? So that looks promising. One can do the full analysis and go consider various details, study possible artifacts and study how it decays with distance. So, it's observable up to 10 microns microns in the first experiment. Now I think people see it up to 20 microns in better samples. One can go through the whole checklist, make sure that we're not fooling ourselves, and everything is in agreement with theory, all the expectations, and the effect is seen only in aligned devices where you get various curvature, and nothing in non-aligned devices where you don't get various curvature, and scales as a cube of local resistivity as theory would predict for Valley currents. It's pretty good, and maybe I'll skip that. So I think it's a non-local response that is a signature of clear signature of charge neutral currents couldn't arise because of any charge effects. Charge effects are always confined to near region near the contacts where you induce current. So that's a good sign. And then there are various questions that this opens up for further investigation. One can try to look at the Chern numbers. One can try to control valley currents better. One can try to detect valley population directly by optical probes, and etc. Right. So I think that's where I'd like to stop and see if there are questions. Yeah.
So valley current within charging current, is it imposed by some conservation law or simply something like electrostatic charging current principle? Why does the valley current why is it charged neutral?
Well, yeah. So it's because they propagate in each valley. They're good, honest charge currents, but because they propagate in opposite directions in one valley and in the other valley, the net current does not transmit charge.
But
one valley
to cancel exactly.
Good. Yeah. So that's a good point. It's because we are doing it without applying magnetic field. So we are time reversal invariant, or we are not, but our material is time reversal invariant, and so there is a time reversal symmetry between valleys, and that enforces the cancellation.
Yeah. So there is different type of pseudoparticles in graphene. There is holes too. So in Hall effect, the effect of Hall it cancels out the effect of electrons. How are signs aligned here? How is Berry current of holes differs from Berry current of electrons?
Right. No, that's another good thing to discuss, which we didn't have time for. If you go back to one of those pictures, so if you do analysis, you see that Berry's curvature is of opposite sign for electrons and for holes. This has an interesting consequence, because the sign of the Hall effect then will not, the sign of this Berry's Hall effect will be the same for electrons and holes. For ordinary Hall effect, when you change the sign of carriers, the Hall effect changes sign. Now here you have to change the sign of carriers, go from electrons to holes, but you also change the sign of Berry's curvature to use the Hall. So the result is that the net sign of this Berry's Hall effect, or valley Hall effect, will be the same for electrons and for holes. And so if you do analysis as a function of carrier density, you predict the same sign of Hall effect for positive carrier density and for negative carrier density for the positional sign change. Yeah.
So how such devices can be used in technology? Can they be used as insulating devices, like for example optronic couplers? What is resistance between terminal 1 and terminal 3, if I recall correctly on the diagram?
Yeah, let's not discuss it. I mean, there are wide-ranging opinions on that. There are people who claim that, just like in spintronics, if you create an information transmission by charge-neutral carriers, you can use it for a variety of applications. And then there are, if you try to think more carefully, you find loopholes. I mean, this is under debate. So let's not get into that because it will be a long discussion. There's another question.
I have a question about the velocity, the formula for the velocity. When we can neglect this second term, and when we cannot neglect this second term in the velocity. The formula for the velocity of electrons in graphene.
You mean this one?
Yes, yes. When we can neglect this
So,
term.
yeah, I think the honest answer is that, well, okay, so I could try to hide it, but by saying that you go, the way to hide it is to say if you go to the bottom of the bracket with this term is 0, then you'll get dominant distribution of that term. That term, if you don't fine-tune anything, then I think this is small. This is small compared to that. What makes it stand out is that it's opposite sign of index, and this is the same sign. And you can use this asymmetry to make the dominant effect because this one will not produce any non-local transfer, just a ordinary local transfer. So here, even though because this term is small, you get something interesting. I think it's small numerically. If you look at things without trying to fine-tune. But cannot stop here. If you try to estimate whole conductivity, for example, from this curve and extrapolate to distances where the excitation pair of contacts or the probe pair of contacts are very close, then you will get a voltage, get resistance which is order HOE squared. So this effect becomes of order 1 in these units at short distances. Yeah.
More questions, please?
Sorry. Yeah.
Okay. What is effective gating? When speaking about effective gating on the theorem, I would, from my opinion, especially so it should be opposite. If you have band gap, you just jump from the upper and boundary with the small tuning of charge carrier density. And here you have continuous.
Yeah, no, that's exactly what my opinion is. When I tell this to my friends, they say, no, you can vary gate voltage continually, and there is a finite range where you are squarely inside the gap. Exactly. Create states inside the gap. It doesn't occur in theory, but the experiment probably there's some disorder inside the gap that creates a finite region where.
I mean the best material for gating is a good insult.
I know. No, I agree. That's what I always do. In experiment. So, for example, here in these measurements, you see that there is a finite range where resistivity is very high, and presumably it's because there is something in the gap that some localized states in the gap in the insulating state. So you cannot jump from holes to electrons by infinitesimal voltage.
If there are no more urgent questions.
So yes, so let's, there is this stuff on education, maybe let's do it after this.
So you want to show the
No, we should go on schedule because we can have
20 minutes behind the schedule.
No, I'm only 5 minutes behind.
Yeah, you're okay.
I'm good. I'm better than the previous guy. But I shouldn't be too much behind. So let's do your talk and then talk about everything
Now
else.
we'll have a break.
Okay.
So we continue in 15 minutes, and anyone wants coffee, there is cafeteria downstairs.
Сейчас я А ну или может восприятно. Андрей есть? Андрей телефон, да.
Ну, на графине я умерла. Да, было очень тяжело. Я поплыла в терминологии английской, к сожалению, увы. Поэтому я потом возьму эту лекцию. Очень интересно. Единственное, что я немножко запуталась опять в терминологии, но это немножко другая вещь. Может, пока потом узнаю, что они конкретно имеют в виду, почему используется одна терминология, а показывается другая.
Знаешь, использовал характеристические классы. Вот эта топология, я ее давно уже изучаю, но я ее изучаю там в полях Янга Милса, вот такое вот. Но я вам скажу такую вещь, я очень много знаю теоретиков, вот я хочу заниматься теоретической физикой, очень сложно найти научного руководителя. Лабораторию найти, может быть, и возможно, но научного руководителя крайне сложно.
Да.
Моему научному руководителю за 80 лет, а Людвигу Фадееву тоже.
Спасибо. Ты полностью разорвался перед партией?
Не полностью. Если бы я полностью
Я не даю, тебе я показываю.
Я знаю.
Я вас пыталась добавить друзья.
Можно несколько?
Извиняюсь.
Просто жалко людей. Считайте, что я там
You ask the best question, you will be disqualified.
Слушайте, я вас правда не нашла. Ну ничего, хорошо вышло.
Сейчас я хотел, ну ладно, может я потом, ладно, я полетел. В этом старом анекдоте.
А вы где-то
Не, я уходила из вашего института. А дальше по-разному и очень не услышала.
вы где-то учились, защищались?
Не защищала. Ну, просто мой научный руководитель очень, старше, да. И мне просто дальше больше неудобно звонить, потому что со мной поговорить. Да, вот я хочу заниматься по науке, но я учу физику. Ну, у меня был просто переход, когда я начала заниматься математикой, изучать математику абстрактную. Да, мне нравится топология. Общая теория множеств. Я алгебраическую, комбинаторную. Да. Потому что, а с кем-то это только теория стыка. Я там переписываю математику все. Да, дело в том, что да. Но это нужно больше заниматься поскольку не надо.
Франция, он получит постоянно.
Постоянно?
Да,
Никита не брался куда? Не красный? Сами
просто часть компактного деньги есть в кармане для положения вещей.
Отвечает на вопрос, да?
Не, ну просто мы начнем потом через 15 минут по порядку рассказать.
Сейчас.
А где Григорий?
Это просто ошибка. То есть можно это, кстати, это не первый раз, что люди видят слово tuition, почему ты думаешь, что это нужно платить.
Это университет платит сам себе, с правого кармана выйдет.
Да. Нет, что надо как ни странно. На телевидении программы некоторые бесплатно. Они иногда стоят что-то там. Ну, не то, не работает. Но я думаю, что те люди, которые
Ну я могу пользу.
сильно как это сделать тоже?
Не знаю, сейчас посмотрим. Я положил тебе туда лаптоп. Ух ты, одна? Поделись. Леня, твой кабель. Держи.
Слушай, оставь его здесь. Значит, давай мы сделаем следующее. Тут пришли несколько человек опять спрашивать про этот Европ, про нужно ли за Graduate School платить деньги, про еще какие-то прекрасные. Я думаю, что это все надо, то есть мы не будем, ну.
Кофе тоже посудите?
Не, я сейчас.
Спуститесь там, смотрите, в кафетерии, где вы работаете, проходите там прямо в торец, там
Да.
маленький зальчик.
Да, я хочу просто договориться с профессором. Значит, профессор, послушайте сюда.
Да. Я могу
Значит,
на твоем компьютере все делать. Мы можем твой компьютер здесь оставить, если.
Не, ну уже все, уже включили, уже все.
Ну,
я хочу про время договориться.
Да.
Давай ты, когда кончишь, ты скажи сам, во-первых.
Да.
Я могу, кстати, тебе это все сгрузить, и ты прямо своего. Давай это так сделаем. У тебя есть эта флешка?
Про что это самое?
Ну вот эта часть, которую я вчера показывал, я там к ней еще добавил какие-то ответы на ожидаемые вопросы, и давай мы ее прямо с твоего компьютера покажем. У тебя есть флешка?
Хорошо. Ты хочешь, чтобы на мою флешку это записать?
Да.
Или потому что у меня уже на самом деле. Или я могу твою флешку вставить, или тебе сейчас. Подожди, я тогда сейчас скачаю тебе свой доклад.
Слушай, Фаядов, я приду с своим компьютером и все сделаю. Не надо мучиться, по желудочку кофе попьем.
Кстати, это дело поставлю. Просто чтобы... еще я должен... А где этот самый... Ты знаешь, пока я не увижу это дело на экране. Видно на экране? Видно. Все. Пошли кофе пить.
Я считал, что вы говорили про функциональную интеграл, да? Там действие получается как квадрат вычислительных уравнений движения, да, просто?
Да, но если вы...
Там внизу есть кофе и печенье. Внизу есть кофе и печенье. Очень большой период будет? Нет, ну, в принципе, уже мы уже прям раскрыли очень здорово. Обед же будет у нас, да? Обед, ну, час будет, получится. Здесь рядом есть лицей, когда делаешь, мы тоже куда-то не переносим. Это немножко пикантно. Он пошел пешком.
Надо микрофон говорить, что услышишь. Давайте я поговорю, а вы будете.
Сейчас нулевой. Фактически здесь получается как-то очень-очень самое. То есть если вот это делить, значит, должны быть, я не понимаю, почему эти штуки должны быть меньше сенситивити здесь, больше уровня экрана. как-то лучше так прорывается. На гум фоне все равно есть, но на гум вот этим повторяешь.
Знаешь что, еще потом туди тоже давай. Нет, а он
Там вы вроде выкладывали видео, вы подписали физик, по-моему, КНУ, а не подписали наш институт. Это же наш институт. И это Институт of High Technology. КНУ. Подпишите, пожалуйста, а то получается, что мы как бы о физике, а не о институте.
Все равно это я все сейчас переделаю, сделаю нормально.
Хорошо, не забудьте подписать.
Останется именно ваш.
Хорошо.
Просто это мы здесь как рабочее название пишем на фестиваль физики, ну и туда, и все режиссеры. Потом я переделаю, будет красиво. У меня будет название на английском языке, на украинском море, значит, что сетап, и какие захиды для прохода сюда. Это будет нормально.
Да, можно будет еще потом логотипы института подгрузить. Потому что картинки у нас есть и у КНУ, есть и у всех институтов есть.
ПНГ,
Есть, у нас хорошего качества есть.
Тогда запишите мой адрес на Смирнов, Укрнета, может быть, сейчас сразу не прислать.
Сейчас не попробую.
Ну, в течение сегодняшнего дня, чтобы я с вечера уже ему буду монтировать материалы, чтобы я уже там выходил.
Я не знаю, когда я сегодня домой доберусь.
Ну, все равно сегодня до вечера вряд ли это тоже, потому что Украина туда, у нас там тоже мероприятие идет. Широко а Смирнов таких там внутренних
Да, я скину наши базовые в хорошем высоком разрешении. КНУшные в высоком разрешении.
Нет, мне достаточно его. Достаточно его, потому что положил, там не будет написано. И ВТ,
yesterday and the weather changes, please?
Thank you. It will be, first of all, I welcome people who were yesterday, and I welcome some new faces. This will be a different subject, related. I'm a fluid mechanicist. You know, I'm the guy who, you know, you open it up and water flows. And when I was young and I was doing plasma physics and you know, thermonuclear research, and then I decided that I go away and do fluid mechanics. And they say, why would you go to do fluid mechanics? I mean, the water pipe works. I mean, no matter that there is no theory of turbulence, and you know, this thermonuclear fusion don't work. And at that point, I realized I actually don't care whether the thermonuclear fusion works, but it's really that bothers me that nobody actually understands how water flows and how wind blows. And so about this mostly elementary things I will talk. This talk will be less popular and less elementary than yesterday. Then I very much encourage you to interrupt me at any moment, and not only to ask physical questions, but also ask what this term means, because sometimes it's terminology which you don't understand, for example, and then you just ask what is this term means and what that term means. And again, I'm speaking in English just because that's the way it was agreed, but if you feel uncomfortable asking question in English, ask it in Ukrainian, that's okay, I will translate it and we'll go forward. The most important thing for me is to get a feedback from you. I really hate it that you don't understand something and you don't interrupt me, right? And again, as I promised yesterday, the person who asks the best question will get the prize today, right? So I very much encourage every one of you, except professors, to participate in this competition. Okay, so what now I'll talk today is why weather changes, why it was cold yesterday and will be warmer today, and what actually drives it. The moment you ask what drives anything on our planet, if you are a fundamental person, you give fundamental answer, and it is, what is the source of all energy in our planet? Sun. Whatever moves, I move here because of sun. You move there, wind blows, water flows, it's all because of sun, right? This is the source of energy in our planet, at least of most motion. But then devil in the details, how actually sun make it moving here and there. So let's see what we can say about it, and let's start from statics. So far I'm considered a fluid, which could be fluid in English is also liquid and gas. What is important that it's fluid. What does it mean fluid? It cannot resist deformation. The difference between fluid and solid, that solid can resist tangential deformation and fluid cannot. It does not mean that fluid applies no force when you try to derive it. The point is that when you try to deform fluid, if you do it sufficiently slow, it always deforms. So resistance cannot prevent deformation from happening. That's the definition of fluids, and we'll be talking about fluids. So gases or liquids cannot stand tangential stresses. It means that if you are in a hydrostatics, your fluid, air, water, does not move, then inside is only a pressure, which is a scalar field, which applies only normal force, which is isotropic in all directions. It's called Pascal law. Right? And so the only law of hydrostatics which exists, it is this law. It tells you that if you have any external force per unit mass, you multiply it by density, it will give you a force per unit volume, and it's equal to the gradient of pressure. A pressure is some scalar function. If it's a system, it's a thermodynamic system, you can get pressure, temperature, concentration. So that's the only relation. It's very interesting. It tells you that whatever forces you apply, it's a vector field, must be equal to a gradient of some scalar field, right? In particular, if the force itself is a gradient of some scalar field, for example, gravity force is a gradient of a gravity potential, electromagnetic force is electric force is a gradient. So in this case, what you get out of here is that grad pi is equal to rho times grad phi. And it's now non-trivial, namely that the gradient of some scalar equal to some rho, which also could be function of coordinate, and gradient of phi. So you ask how actually, if I know this potential, how my density would be distributed. So you take a curl of this equation, just act by operator curl on it, and you get the simple statement, which if you translate it in the simple theorem which tells you that the gradient of rho and gradient of phi must be parallel. Namely, if your gravity changes vertically, your density also changes vertically. Right? If your density cannot change horizontally, there would be no hydrostatics. That's the only law of hydrostatics, which is very intuitive. Yeah, you would probably guess it without calculation. But it immediately tells you why wind blows. Why this statement tells you why wind blows on our planet where we live. Wind blows means that there is no hydrostatic equilibrium. So what creates wind? It's a horizontal gradient of density, usually a gradient of temperature, which produces a horizontal gradient of density. Because the force is vertical, it cannot prevent horizontal motion. So if you produce hot here and cold here, wind would always blow. No hydrostatic equilibrium. That's it. 3 minutes and you already know why wind blows. Right? Good. So one source of motion is a horizontal gradient of density or temperature. Because our sun warms our planet differently on different sides, it must create the flows. Right? There's no way to avoid it. But there is also this is a statement that I say, but there is also a vertical gradient of temperature, and it's created by the fact that the sun radiation hits air and land differently. Most of the sun radiation, particularly if there is not much clouds, is absorbed by the land. That's why, as somebody who was yesterday, and we discussed why Aristotle believed that the higher you go, the warmer it gets, and in reality the higher you go, the colder it gets, is because most of the sun radiation is absorbed by the earth. It's absorbed by the earth, which means it's warm air down there and it's colder air up there. But the warm air is less dense than the cold air, right? So what we have a gradient of the air density, which now vertical, that's okay. It's vertical, namely it could be compensated by gravity, but it's inherently unstable. Because if you have light here and dense here, then it actually want to exchange and put dense down and right. Well, that's true, but on the other hand, you may ask what actually the criterion for this instability. So if you look at our temperature and how it depends on that, which is a vertical coordinate, such the height, then we can substitute here an equation of the state of an ideal gas, and air is very much ideal gas, and then you get how pressure depends on the coordinate. It's some law which is expressed through the mass or the medium mass of the particle, gravity, acceleration, this factor, and this factor is on average in our planet we lose 6.5 degrees per kilometer. This is how fast it's getting cold as you go up. It actually goes not all the way this, you go up to some 10 kilometers and then it inverts actually and is getting warm. But with first 10 kilometers, which is called troposphere, then we lose 6.5 degrees per kilometer. You go 2 kilometers high into the mountain, you on average get 12 degrees less. So good. But is it stable or not? How is it enough, this gradient, to produce a vertical motion and instability? Let's do the calculation. It's pretty simple. So what you say, if I take what is this stability? Stability always, since Archimedes, we do stability analysis like this. We say, okay, here is my state. I have a warm air here and dense air here. Let's make a small change. Let's say I take just some random motion, produces my parcel of air, just moving from here to here. And it moves it in such a way that it keeps its density from here, it keeps its temperature, it keeps its density, but of course, as it transforms to this place, it will be under new pressure, because the pressure here is larger than pressure there, right? This is precisely this rho g h gradient. So now we say, on one hand, this pressure want to return, but on the other hand, the fact that it's now in the environment in which it's lighter than the rest, it want to go up. But the pressure want to return it down, and the competition between these two things creates whether it's stable or unstable. Or in other words, you may say, this is a small change in the thermal energy which I get if I exchange these two parcels, and this is a small change of a potential energy, right? So if I take this something moves a little bit, it gets more potential energy, but it gets less thermal energy. And then you say, if this would be larger than this would be stable. If this would be smaller than this, it would be unstable. So gravity would win, and the light element would go up. Then you put numbers, you say that the vertical gradient of temperature from here, dt divided by dz, it will be g divided by cp. So you calculate, you put numbers, it's pretty easy, we know all this, and we get 10 degrees per kilometer. What it tells us? It tells us that our atmosphere of the planet is on the verge of instability. Because what we have in our planet is on average 6.5, right? But what it means on average? It means that in some places it is 10, in some places it is 5. In some places it is 15, in some places this is 3. In a big city, just try to go through the big parking lot into the park. The change of temperature is 3-4 degrees immediately, you feel it, because the albedo, the reflective index of the surface is very much determining the temperature. I mean, I live in the campus at the Weizmann Institute. This is a very green area in a very hot country. And every moment I just exit my campus and I go into the city, I feel plus 3-4 degrees immediately, and it's summer, really, you feel it. Okay, which means that there are many places where our gradient is not this, but actually in extent of it creates vertical convection. And it's everybody who try to fly kite or balloon or whatever knows that there are places, particularly in a parking lot or in a forest, where we would expect more convection in a city. In the parking lot, because it's hot, and then at these places, and particularly when you try to fly your kite, then you immediately notice that when you go on a green grass or when you go on asphalt, it's totally could be very much different. And if you fly a small plane, which I was fortunate twice to do that, and you go like at the height of a kilometer or two, it's really that's there you also feel this area, particularly when you fly from Tel Aviv or the sea or on land, then you immediately notice how different is convection part. So if we sum this up, is that on our planet we have horizontal gradient between equator, which is more heated by the sun than this. We also have a night-day parts of the planet. It's another horizontal gradient. So we have big winds on a planetary scale always circling our planet. They always do. It's a persistent part, and there are also patterns of circulation over there. And we have this something which works, this is what creates this big flows, and we also have this scale more or less of few kilometers up to 10 kilometers, which is the size of a troposphere and on which convection acts. So now we say that we're absolutely sure that sun drives motion on our planet of the scale of 6,000 kilometers, which is a typical planetary scale, and of the scale of 10 kilometers, which is a typical height of the troposphere. But the weather does not care about 6,000 kilometers and about 10 kilometers. Weather is something which is determined on a scale of hundreds of kilometers. That was the typical size of weather fronts. So we are interested in what are the motions on our planet, and in particular, this is off side of California, and then you can see a big vortex. Maybe here it's even better. You see this big vortex, which is a typical. This is in Oregon, probably, or is it Canada? This is something like maybe 700-800 kilometers, this vortex. And you look inside, you see smaller vortices, you see this kind of structure. It is this kind of structure, which is 200-300 kilometers, which really determine whether people in Seattle would get another day of rain or they will get a rare sunny day. So what is interesting now for us to understand how this motion of this scale gets their energy if what sun does, sun drives very large scale and drives very small scale. Then of course we go and we measure, what we do, we measure a spectrum of energy distributions over scale for a wind. And that's the result of this measurement. It was a very beautiful set of experiments, not experiment. There was a commercial liner which was driving from Chicago to Honolulu and then back. As it went, apart from everything else, passengers, it has a scientific equipment sticking out and measuring the wind speed. So as you go and you measure wind speed as a function of coordinate, and usually a jet flies much faster than the air, which means that for when you fly a big plane, the wind more or less has a frozen field. So you can really measure it in your fast-moving reference frame, and then you can reproduce the dependence on your velocity of the air as a function of coordinate along your path. Now, if you know some function as a function of coordinate, you can Fourier transform it and get it as a function of a wave number, and that gives you a spectrum. So you see a wave number, and that's a planetary scale which is about 1,000 kilometers. Okay, you see this is inverse meters. So if you look at inverse meters, then you have 10 to 4 meters, and then you have something like 10 meters, and here you have something like 100 and then kilometers, etc. First of all, and they are the same, they just shifted one to another to distinguish them. So you have a zonal wind, namely the wind which goes in this direction, and you have a meridian component of this. So this was a device that was measuring two components, because Earth rotates, so you really want to distinguish the wind which goes in the direction of Earth's rotation and the wind that goes that has a component perpendicular. First of all, what we can see is that it's a pretty uniform distribution of energy over the wave numbers, over the scale. So we don't distinguish that somewhere here there is a source of energy and here is a source of energy. It's a pretty kind of a uniform distribution. As always physicists try to do is to try to get, is there any law by which we can describe? And then people match it by two power laws. One is more or less k2 minus 3, and another is k2 minus 5/3. And in a minute we start talking about where scaling law, where these powers can come from. But the point is that it is this which we want to understand. How energy, which we know produced on this end and on this end, how it gets into this intermediate scales where this vortices really influences the rest. So here is the problem. As it's formulated, all atmospheric flows are driven by the gradients of solar speed. Vertical gradients work on a scale of 10 kilometers. Horizontal gradients work on a planetary scale, all the way up to 10,000 kilometers. Weather is mostly determined by intermediate scales, where these flows get their energy from. You say, well, it's a nonlinear system. In a nonlinear system, different Fourier harmonics must interact. If I produce two vortices of a given size, they can easily produce big vortices, they can easily produce smaller vortices. And then it should not be surprising, just like I said, should not be surprising that intermediate scales are excited. Yes,
I want to ask about the dimension on the previous graphic. Y-axis has the meter cubed by second square. So for Fourier transform of meter squared by second square, which would be energy, the dimension must be meter by second square.
Yeah, I'll answer it. Let's see. The energy is meter squared per second squared, right? I don't write grams here. But then you do it as a spectral density in a Fourier domain. So if I integrate it over the Fourier spectrum, I will get my energy, which would be meters per square. But the integration over k, it's like multiplying by another. So it's a spectral density, not the total energy. You integrate the spectrum, you would get your total energy. Okay. Now,
can I ask you about the horizontal axis?
The horizontal axis here is a wave number. It's in radians, namely the angle, divided by meter. So in a sense, you can say this is equals meters.
So 10 to the power 4?
10 to the power...
small perturbation.
What do you mean small perturbation? No, 10 to the... No, this is a large scale, this is a small wave number, this is a large scale. Sorry, this is already in meters, yeah. I apologize. So this numbers is is already meters, and even though it's, wait, I mean, this is wave numbers, namely that this end is a large scale, low wave numbers, and this end is a large wave numbers, small scale.
Can you return to the previous slide before that? And no, actually, when you have DE on DS. Yes, what's DS?
Yeah. S is an entropy. So in a sense, what I mean, you assume that you do it adiabatically, right? So and then you ask, okay, if I now move this piece from here to here, but I kept its temperature, namely that I kept its entropy. But it now has a new pressure which is equal to the same pressure which is on this height. But it has different entropies. So what I want this overall to be, but there are two results. I'm at higher pressure, it tries to compress me. But I'm at a lower temperature. Lower temperature means lower density. So that's two competition, and that's this formula express which one wins. Because this is a very large gradient, then you would have really thermal energy winning, and it would go up. Okay, now the problem. So why it all it is a problem? If it is a nonlinear system which we drive at small scale and at large scale, it must just by nonlinear interaction fill this whole scale. The point is that fluid acts in the following way. If you have a really three-dimensional turbulence and you create big vortices, that what they tend to do, they tend to break into smaller and smaller and smaller pieces, and we call it direct cascade. Direct, namely that it goes from low wave number to high wave numbers, and this what is more or less you expect from turbulence. That you create some, for example, you drive your car, it leaves behind vortices which is a typical size of a meter, 2 meters. That's what the typical size of your car, typical height. And when you just measure it 20 meters after your car passed, then you see that it's a lot of very small vortices produced by these big vortices. Because eventually it would go to very tiny small scale vortices which dissipate energy due to viscosity. Two-dimensional flows, planar flow, act completely different. In this planar flow, when you create a big vortex, it does not have a tendency to break into small vortices, just go like this. But in particularly, if you have two mid-sized vortices going like this, and they meet each other, right, then they tend to create one big vortex. Particularly, if you imagine that you have vortex which go like this and vortex which go like this, right? Then this middle part where this goes this direction and this tend to cancel each other, and then you have one big envelope vortex. Here it goes this way, here it goes that way, and here it cancels in between. So what planar flows do, and it took some time before people realized it, that it creates inverse cascade. Namely, that the energy which is inputted at small vortices tend to organize into larger and larger vortices. It's an interesting story what actually brought this. Probably Anzager, who did many things, I mean, probably deserved 3 Nobel Prizes for his work, but at some point he realized that planar flows, particularly atmospheric flows, and as we know, particularly on large planets like Jupiter, where you have this big vortex which just lives for 400 years, they tend to produce these big vortices or big large-scale flows. And then he started to think about it, and that's how he came to this notion, which eventually was called negative temperature, when system tries to create large-scale structures out of a small-scale noise. But in turbulence, it took up to 60s, and in particular, my teacher Zaharov and Bob Crackman in America, they realized that there must be an inverse cascade. Namely, if you constantly feed energy towards small scales, then the small scales, if they are planar, they would create larger and larger vortices. And the mechanism, basically, it is this which I presented to you. So now let's look at this problem from this perspective. So if we would have a 3-dimensional turbulence, which we excite on this scale of 10 kilometers, it want to burn its energy at small scales. It would really, this, big convective pattern which has, 5, 7, 10 kilometer scale, would break into vortices which is 100 meters, and then 10 meters, and then 1 meter, and eventually all this cloud turbulence which I talked yesterday, it is a result in particular of this process. And when you measure in the atmosphere, you see that fraction of millimeter is actually the size of the tiniest vortices that you can really measure and observe, and smaller scales are already killed by viscosity. So doesn't have any tendency to give this energy towards larger scale, because the convection is three-dimensional, right? Now, on the other hand, on the other end, you have this creation of big planetary scale flows, which are driven by the planetary scale gradient of temperature, right? We have equator pole, we have day-night sides, so we create these big flows, but they are planar. They practically have only horizontal component. Because if something exists on a scale of 1,000 kilometers, and the depth of your fluid layer, which is our troposphere, is 10 kilometers, then it's practically shallow fluid, and it creates only planar motion. But planar motion don't break into small scales, right? And that's basically what created this problem. The more you know, the more problem you create. So before people knew about direct and inverse cascade, it seemed natural that just by driving energy at small and large scale, you would feel on scale in between. The moment you understand that your large scales are actually planar, and they don't want to create cascade towards small scale, and your small scale are three-dimensional, as they don't want to create inverse cascade to large scales, then you're in trouble. You need somehow to explain how you manage to feel all this intermediate scale. And what we're talking about, it's not a theory, it's some experimental work which sheds some light on it. And of course, the atmosphere, it's a very, very complicated phenomenon, and what physicists usually do is treat some very simple, basic, fundamental aspect of it. And this is, again, this illustration how three-dimensional turbulence like. This is the flow, you put here a grid, and you create, now you modify your flow on this scale. This is the opening, you see, this is opening, this is a closed part. And then you see how it produces small scales. This is this direct cascade. Now, if you look at, this is already our experiment, you create a thin layer of electrolyte, you drive currents through it, you put small magnets below. So what you create as a result of it, you create Lorentz force, you create this small vortices in a very thin layer. This typical size of the vortex is 9 millimeters, typical depth is 2 or 3 millimeters of this layer. And then you see how out of the small vortices you create bigger vortices and eventually one logical flow. So that's inverse cascade of a two-dimensional turbulence, right? So it's just an illustration that what I hand-waved is really happening in nature. And again, any jet would create the small scales. Again, this is a two-dimensional flow, which now it's a grid, and you have small vortices here, and then you produce larger and larger vortices. So that's the difference between direct cascade and inverse cascade, and the one analysis. Now, what about scaling? Namely, what we would expect would be a power law of energy distribution over the wave numbers. It's very easy to guess. Well, which took a genius of Kolmogorov, but 60 years after Kolmogorov, it's very easy to guess, and I don't need formulas for it. I can again hand-wave my way. So what I'm saying, let's look at a given, I would speak in R, not in wave number space. That's probably more intuitive. So I'm interested in how much energy is in the vortex which has a typical scale R, right? How I would quantify it? I would say, let's take point, another point at the distance R, and measure typical velocity difference between these 2 points. This velocity difference is created by vortex which is of this size. If I have a bigger vortex, it doesn't create much energy, much velocity difference at these 2 points. It just transfers them together. If I have tiny vortices, so their influence on this point and on this point are already cancelled because they are very tiny and there are many of them. So if really I want to measure the velocity difference, this would be a good characteristics how much energy is in the vortices of this size. So the typical kinetic energy, it would be of the order of the velocity difference at this distance squared. But I want to understand how energy cascade would go. Namely, that I have somewhere a source at some scales, and I have somewhere a dissipation at some other scale, and at a given scale, I must transport energy, transfer it. So interaction of of this scale with a little bit smaller scale or larger scale would lead to energy transfer. So I need to take energy density and divide it by a typical time which I would expect my interaction to happen. What is beautiful about fluid mechanics is that it's mechanics. And the time is always distance divided by velocity. That's what I like about it. Never problem with time. So its typical distance is again distance r. It's a kind of circumference or diameter of my vortex. And the typical velocity is v. Give me a typical time. And I want that the energy per time, it's a rate by which I transport energy, would be constant, would be equal to the flux of energy in which I put my energy into the system and the rate of dissipation by which my system dissipates energy. So if I require that this is independent on r, then I would say that my delta V cube must behave like r in the first power. That's what Kolmogorov did in 1941 in Obukhov. They did it at the same year. Never got Nobel Prize for it, which is a shame. And in a sense, you can make it formal. You can actually derive it from the equation of fluid mechanics, and you can do it for both 2 and 3 dimensions. Of course, there was nothing about dimensionality here, so the scaling must be the same, but the factor is different. So if you formally say that delta V, now the difference of velocity measured here, taking cube of it and averaged, namely that you just look at turbulence, how technically you do. Just take 2 points and you measure all the time the velocity difference, and then you average over time the cube of it. Normally, what would you expect it to be? You expect it to be 0. Why? Because it's delta V. Delta V on average, of course, 0. It does not move in any direction. The cubic moment or any odd moment is not invariant with respect to time reflection. It tells you that if I make a movie of my turbulence and just by mistake screen this movie backwards and measure the same delta V cube, it would change its sign. Which means that if you are an expert and this delta V cube is non-zero, you can tell whether it's the right direction in which you are shown movie or wrong direction. Because turbulence is inherently irreversible. You put energy and it burns energy. And this is a measure of its irreversibility. But what is interesting, if this is epsilon is a positive quantity, which is the energy burn rate, how much it dissipates energy per unit time, then in 2 dimensions it will be negative, and in 3 dimensions it will be positive. And also the factor will depend on dimensionality. Here you can put 2 and here you can put 3. But the fact that its delta V cube is r does not change. Now, if you're interested in what is delta V squared, is r into the power 2/3. Now, if you Fourier transform it, you will get k minus 5/3 for the spectral density of energy. And this seems to be precisely this scaling which we observed over here. It's k minus 5/3. So the beauty of this picture is that it coincides with the scaling which we would expect just from the idea that we have an energy cascade over here. But it does not tell us which way this cascade goes, backward or forward. Because for this you need to measure not a spectrum, which is a Fourier transform of a second moment. You need to measure third moment, which would have positive sign if you have inverse cascade and negative sign if you have direct cascade. And so that's how you try to measure it. And then again it is this spectrum. And then people went and then people measured the third moment, and they found that it has a wrong, a negative part of it, which means that the energy goes this way from large scale to small scales. And of course, it's notoriously difficult to make this measurement in the atmosphere, and this is now what I've shown is actually laboratory data. In the atmosphere, you really need to have much larger statistics. The higher the moment of any random quantity, the more statistics you need to get it. Now the point is that it's something that you really measure which is not pure turbulence. It has some kind of a large scale flows which goes around it. And so let's see what experiments would show us. And this is the oldest experiments which were done
in Paris by Patrick Tabelin, and they use magnets like this, and they drew current through the electrolyte. And so when you look at the energy spectrum, you see that initially it appears this peak at large wave numbers, which is the size of the magnet over here. And with time, it really builds up this spectrum. And if you multiply it by k to the 5/3, you see that it's a constant. So it's really this k minus 5/3. And you know that in this setting, in a relatively thin layer of a fluid, it is an inverse cascade. You see, it goes from large k and it develops towards smaller and smaller k, larger and larger scales. So now, I mean, at this point, I just want to stop you and realize to what extent this is strange. So it's turbulence. It's a very random chaotic motion, and it acts like self-randomization. Namely, out of small, noisy vortices, it creates something big and much more coherent. That's why it took so much time actually to get to this point, and I'm not sure that we completely explored all the consequences of it for fundamental physics. But as a result of it, as this inverse cascade reaches the size of your system, it tends to create one big coherent vortex. And that's precisely what was observed, that already pictures that I've shown, that if really in your system the dissipation is small, this cascade goes all the way to the box size, and it creates this big vortex. Of course, there is a lot of turbulence inside this big vortex, but it's clearly distinguishable large-scale coherent flow produced out of this random picture. And then you can study this vortex and how it develops, and then you can really analyze this turbulence. Now you know that it is inverse cascade. If it's inverse cascade, its third moment must be positive. But if you just measure it, it's negative. So you need first to subtract the mean flow, get only fluctuating part of the flow, and then you look at the third moment, and then it has a right sign, which is a positive sign, which tells you this is inverse cascade. If somebody could do it for atmospheric turbulence, we would know what actually is the sign of the flux there, but so far we lack the data. So we go and we go further, and we can also analyze this vortex, and we did some beautiful theory relatively recently, which tells us what is the profile. This vortex is fed by turbulence, right? So I have the big vortex. Of course, it's large and it has bottom friction. It's always a bottom in any two-dimensional system. It's not two-dimensional. It has a third dimension. It's a bottom, and it has a friction of the bottom. So to have this vortex, you need constantly feed it and turbulence feed it. So what this vortex does, it absorbs the small vortices in a way to reinforce its overall rotation. And then you can, out of this, you can build a theory and predict the shape of this vortex, and it is our theoretical line, and it is in experimental data. We're very happy about it. It's just recent, last year work that was published. But now, it's all was about very, very thin layer, in which we excite vortices which is already have this size much larger than the typical width. But what happened if we have this convection, where we actually excite a typical scale of motion, which is of order of our height, and which is also has this size comparable to its height? What happened? Could we have some leakage of energy towards larger and larger scales, which would create an inverse cascade out of it? And it was very, I would say, heroic numerics, where people just took this system like this, and they have this LF is a forcing scale. So you can vary forcing scale relatively to the system height. And then they look how energy of the system behaves as a function of time depending on this ratio. What is on this scale? It's a ratio of this towards this. So energy grows linearly with time. And then eventually, this tells you that there is an inverse cascade. Inverse cascade means that you don't burn energy at small scale by viscosity. You build up energy by creating larger and larger and larger motions. At some point, it reaches the size which is of order of your thickness. And of course, it kind of want to stop, right? So you have this energy continue to grow when this is 1/8. this is 1 over 8, this difference. Then it's 1 over 4, 3 over 4, and when it's 1/2, you see that energy is getting flat. It does not grow. Namely, to put it in simple words, when the typical scale of your vortices is about half of a typical height, it stops getting energy towards large vortices. It does not consider this setting as a flat two-dimensional planar flow. It's already three-dimensional, and three-dimensional flow burns its energy in the small-scale viscous motion. And this is time, right? This time is about 2 months of non-stop computation on the European supercomputer. At that time, that was 2010. It's still comparable to the Japanese has better facility, but not by much factor. So it's really, to make that long calculation, it's a heroic effort. It's 2 months of non-stop work, and there is no non-stop work on computer. It crashes, it stops, we need to restart it. But nature is much better computer than what we do. So you can do experiments, and experiments can run longer than your supercomputer can run. And that's what Michael Schatz and Canberra did, and that's already our work, which was the next year, 2011. So what we did, we took, again, this setting, you have electrolyte. The only thing we really wanted to have our friction very, very small. So the setting was like this, that we put 2 layers of fluid. One was dielectric, which acted as a lubricant, and another was an electrolyte in which we really were driving vortices. So these vortices were using this lower dielectric, which did not move, just as a lubricant so that we decrease the friction. And then what we did is that we really started our magnets, and this is precisely the same setting, namely the size of the forcing is 1/2 of the size of my box size, where we expect, according to numerics, totally three-dimensional motion, and that's what we see. This will look from above on our, this is experimental snapshot of the velocity field. This will look from above, and this is a look from a side. You see that it's really three-dimensional motion, and when you look here, you see that this is more or less something where you don't see any large-scale structure. It's a set of small-scale vortices. And this is the magnet size. And the magnet size is this one. This is 5 seconds, which is approximately, this 5 seconds of a real physical experiment, which corresponds to this 2 months of supercomputer. See how faster nature computes than we do. It solves earlier Navier-Stokes equation all the time, but do it really fast. And then, but because nature does it so fast, we can wait for 20 seconds, which would be 8 months on supercomputer. And then we see that something else happens. That the flow slowly rearranges itself in the following way. It suppresses very much this vertical component. Not completely. There is something left, particularly at the boundaries, there is something left. But it's very much planar, and you clearly distinguish a large-scale flow which appears over here. So apparently, what happens is that there is a small leakage of energy which goes from these vortices into larger and larger vortices. But the moment some large vortex appears, it's already planar. And it feels like if it's planar, and as long as it's got another planar vortex, it wanna create even larger vortex. So it starts not a cascade in the sense that we don't have a constant feeding of all our energy over there, but it tends to create larger and larger vortices. Now, what these large vortices do to these small scale guys? Why? Not only we see this big vortex, but we also see the planarization of this flow. Before we had this type of motion, vertical stuff, and now when we started to get in this big flow, we see that inside it's getting more and more planar.
Larger vortex is more powerful and its horizontal component overwhelming vertical components.
That's right, but we can always subtract this overall from there. This vortex is actually slow comparatively to this. It has much more energy because it's large. But the point is that this vortex is not two-dimensional, it's planar, namely that all velocity is horizontal. But this horizontal velocity strongly depends on the vertical coordinate. And then we did experiments to see it. So that's how this picture looks like. So you see this now a picture with this big vortex, that's how it's looked from the side. What we expect this big vortex to do, this vertical gradient, because we have an open boundary here, and we have a bottom here. Even with lubricant, it's still a bottom. So we expect that our velocity of this big vortex grows with a height. And it creates shear, namely the velocity in this direction depends on this direction. Now, to every vertical vortex, it does the following thing. It distorts it immediately. So if I have this vortex, it turns to distort it this way. But the moment it distorts this vortex this way, it makes its scale much smaller, and it's getting a strong friction between this part which moves this way and that part which moves that way. So out of this vortex, I create this type of very elliptic vortex in which is a very strong viscous friction which kills it very fast. So what we expect a large planar flow to do, it expects to very strongly kill this type of vertical motion which is and then the moment you kill a vertical motion, you make your flow two-dimensional, and two-dimensional flow want to get energy towards large scale. So what the big vortex actually does, it provides its own energy supply by making your three-dimensional turbulence locally two-dimensional, right? And this is something which kind of it's a shame. I mean, as a theoretician, I was supposed to really foresee it and build a theory for it. I had value ideas, and actually my role here was saying to experiments, just let's add more water and see what happens. Because they were always experimenting with very thin layers because they wanted it two-dimensional. And say, let's add water, and say, well, you add water, you have three-dimensional, nothing interesting. And eventually we've seen that even for a very sufficiently thick system, it still locally organizes itself as a quasi-planar flow. And then, of course, you want to really study it in more detail. So what we did, we make this setting. We produce this type of turbulence. But then you can always produce big vortex yourself, not waiting until system produces by this inverse cascade. You can take a big magnet and put it over there. It's electrolyte with a current going through it. So the moment you take a big magnet and put it in, creates a big vortex. So in a sense, we can really create big vortex, see how this big vortex influences, and we can remove our magnet, how this big vortex decays, and that's what we did. So we have turbulence, then we put big vortex, we really see that it makes it planar. We can measure vertical component of velocity, we see how it actually goes down when we put this magnet, then we can remove this magnet over here, we remove magnet, and we can see how it slowly returns to this three-dimensional because system did not create its own big vortex here. So in a sense, what I am saying that all this picture, you can really make it detailed quantitative analysis just by controlling things, by putting vortex, by removing vortex, etc. So in a sense, I would say that we are now pretty confident about the fact that we really can have in this system an inverse cascade. Again, we measure third moment. The third moment is this delta V cube. And remember that when it's positive, it means that it's an inverse cascade, and we really see that it's an inverse cascade. So this system, after the big vortex appeared, really gets energy that you always inject by your small magnets always works, right? You always inject this energy, and it always goes towards large scale, even though the system is thick. It's not something that you produce a planar motion. So it's not, at this point, this was considered kind of nice curiosity. And just consider how much simpler our, it's salty water that we use. So we have a narrow layer of salty water with a current, and in a very controlled laboratory experiment, how different it is from this mess, which is a turbulent atmosphere. And so people say, well, kind of nice. This is part of this puzzle of this mosaics. Probably sometimes this thing happened, and some referees say no, that would never happen because in nature there is much more complicated setting. And then the co-author of this work, David Byrne, he graduated. He was a PhD student who actually did this experiment. It's always PhD students who do science, by the way. If you're interested who does science, that's PhD students who do science. So David graduated at 12, and then he went to work for meteorological business, and he got hold on the meteorological data. And among this data was something which incredibly brave people flew the small plane in and out, which is a fortunate part of it, out of two big hurricanes. So there is a big hurricane. One was Isabel and another is Fabiola. This is Isabel. This actually was a huge hurricane. It diminish the territory of United States. The part of the state of North Carolina does not exist after this hurricane. You don't care about the territory of the United States, but my son just lived in North Carolina at this time. It's a really huge hurricane. And so this is the track of a flight. So they took a flight and they several times flew through this hurricane, doing the same thing that people who flew from Chicago and around it. They measured wind velocity inside. And it's now huge, I mean, it's a hurricane. And incredibly, they did it several times on different heights. Okay? And they collected this data, and this data was, they're still there, there's a lot of data. And they waited for somebody to make sense out of it. And then David, because he did this work experimentally before that, get hold of this data and say, okay, let's look at this data, let's analyze the flux of energy. Because if I can take velocity field and I can calculate the third moment of a velocity difference at a given scale, and I can see that as a function of scale it behaves linearly, then by the slope, whether it's positive or negative, I can understand whether in this hurricane the energy goes from small scale fluctuation to this big hurricane motion, or it's the other way around. This big hurricane motion actually dissipates its energy into producing smaller and smaller vortices. And that's what they did. It was just published last year. So you see, these different colors are different heights. So as you go, it's lower height, 88 meters. You need to be incredibly brave to flew into hurricane. It's over the sea. It's the height of 88 meters. You know, just little, you know, indiscretion on your part, a big fluctuation of the vortex velocity, you are in the sea. 88 meters, it's really kind of, it's just unbelievable when you look at this data. The point is that you see a negative slope all the way up to 137 meters. It's a little bit more safe, but the data are more or less the same. And it tells you that this is direct cascade. Namely, that this part of the hurricane, which is the lower line, is more or less giving direct cascade. Namely, that the energy of this motion it goes into the energy of a small scale. It's actually the part which is less energetic. As you go higher in the hurricane, it's a more energetic part. So as you go to more energetic part, you see that it's still a very decent straight line. It's really very good. But it changes the sign of the slope. And the sign of the slope is the direction of the energy cascade. This, by the way, Kolmogorov realized it. You need to take a certain moment and you get useful. So you see a transition between a direct cascade and inverse cascade as a function of height. So when this hurricane is really very, very intensive in its middle part, it's where it gets reinforced by small-scale fluctuation. So we're now talking not about large-scale weather pattern, but of a very local, well, kilometer, a few kilometers, 10 kilometer size phenomenon, but the mechanism is the same. Very strong planar motion provides its own energy source by rearranging small-scale turbulence so that this small-scale turbulence gives energy to the large-scale flow. And this precisely this positive slope which tells you this. They actually took hold of another data which was a Fabian. Isabel was a big hurricane, Fabian was kind of a mid-size, but again it's the same tendency. Small heights you see a direct cascade, then at some height you see that this is actually, this third moment is practically zero, which tells you that this is a region which you don't have energy cascade, because energy cascade is what gives the system irreversibility and what gives non-zero third moment. If the system is locally time reversible, the third moment must be zero, because when you reverse time to minus time, velocity reverses to minus velocity. So in a sense, this is beautifully shows that in nature you can really see in such a messy event like a big hurricane, you see this incredibly strange and interesting physical phenomena of inverse cascade. That the small scale fluctuations really feed energy to the large scale flow. For sure, it could not be the main source of a hurricane energy. The main source of hurricane energy, of course, it is this huge convection and all this condensation and evaporation which happens inside. But it's a probably important part of creating a relative balance between different heights of a hurricane, and in particular it shows that it works. So I'm going to finish at this point and give this kind of a summary. So first of all, this what we call by physical terminology, these big vortices we call spectral condensate. And basically this is the main conclusion which I want to draw from it, that the small scale turbulence and the large scale vortex can conspire together to provide for an inverse energy cascade. So something which you would not expect to behave like a two-dimensional flow really does as a two-dimensional flow. Okay, and at this point again I want to ask for your questions, and this will be a prize for the best question. Yes?
Slide with planar vortex, you said that big planar vortex had a lot of little scale vortices, and that would be big quantity of little vortices.
Yes.
So with the time it should be had to be less of this. It should be less small.
Less of small scale vorticity?
And just to know about what it should be less of, I mean, it should be self-organized, this
in a sense, it's a way of self-organization. So you have the small-scale vorticity. It starts to create a bit larger vortices. These large vortices tend to distort small-scale vortices and kill these vortices which have this vertical component. Vortices which have this component are not influenced by the large-scale flow. It just transports it. But vortices which has vertical component of velocity, by this shear flow, they are distorted and killed. So as a result, your big vortex organizes your small-scale turbulence so that it would be planar. It would be small-scale turbulence, but there will be less of vertical component to it. That's what it does. It's a way of self-organization. Non-linear system could do self-organization, but it's interesting that three-dimensional flow by itself don't do it. But the moment you restrict it in vertical direction, it starts to be possible.
My question is about this, if we have a lot of time, it tends to be no small turbulence.
We always produce in our setting in the lab, we have the small magnets, we have current, we always produce small scale turbulence. This turbulence mostly it feeds the big vortex. If we switch off current, the system dies very fast. Nothing moves until you drive it, that's for sure. Right? And particularly this big vortex, it has a friction. It's small, we have lubricant, but it's final. So it's always fed by feeding small vortices into the system. What big vortex does, he takes the small vortices, kills all of them which are vertical, leaves all of them which are horizontal. Those which are horizontal feeds its energy to this big vortex. Right?
And if we just end with this small vortices, it should be really...
If you stop producing small vortices, your big vortex dies. He gets its energy only out of small vortices. So returning back to weather, we believe that in this 300 kilometers big vortex, which you observe somewhere, is some part of it is produced by 10 kilometer size convection. Which if you would ask somebody 10 years ago in the theological community, they would laugh at you if you would just say it. Right? Because it's a three-dimensional turbulence was supposed to burn all its energy at viscous small scales. Yes?
I have a question about the computer simulation. So you mentioned that it requires even several months, so up to 1 year of supercomputer time.
Yeah.
But then what is the size, what is the smallest size, what is the smallest volume of the air mass that is used in this calculation? Or in other words, what is the size of the grid? And if you increase the size of the grid, the step on the grid, that supposedly should lower the amount of computer time that you require. But then will you see the same hurricanes or the same vortexes produced in the simulation?
Nobody ever, I mean, for the next 10 years, 20 years, I can guarantee nobody could be able to numerically simulate hurricane, even a part of it. What now is possible in three-dimensional flow is to decently model a flow in a in an aquarium with a small fish. That's maximum that you can do for a water, for the viscosity of water. Now, what these people did numerics over there, they really try to do as an experiment, namely, you have something like half a meter, layer of 3-4 millimeters of water, or 5 or 6, and viscosity, which is the viscosity of the fluid. This they can do they can model 5 seconds of an experiment by 2 months of supercomputing. Nature is better still. Right? Yes.
Well, I want you to provoke you in some way. So it seems to me that you don't tell us all the truth. Because you always, all the time you speak about transformation of energy, yes? But energy, kinetic energy, has only positive sign, yes? But when we see big vortex, it has a definite sign, you see? It can rotate in one direction or other direction. So when you see, well, short scale turbulence, it has no direction, preferable direction, yes?
Yes.
But it appears in the end.
Yes, so very good question. So indeed, I have magnets, and we are very, very careful. We have 900 magnets, and 450 of them are north, and 450 are south. Namely, when we drive current, we produce 450 vortices of this size and 450 vortices of this size. At the end we look, we see one big vortex going this way, like as if I would have. And then I say to my cousin, Misha, there's something strange, how it knows which way to go. And he said, because you know, theoreticians always ask about symmetries, and experimentalists always know that the set truth is that you change your walls of your container a little bit, your vortex go other way around. Which means that it's something which happens like you do a magnetization. You lower temperature, you see your magnetization looking in some direction. It's just a random choice of a random initial condition. In this particular case, the vortex could appear in any direction. In Earth, we always have a direction of the rotation, and it always the big flows which appears, they know which way to go, because at Earth always have this cyclonic vorticity and anticyclonic vorticity, anticyclonic, which is opposite, completely different. But in the intermediate scales, I mean, the latest thing about it was really made everyone surprised. In Santa Barbara, they did experiment on a scale of about a meter by meter apparatus. They did convection over there. And when you do convection, you have this, you know, big vortex which is like this, right? And of course, it's so far, I mean, nothing wrong, I mean, you can kind of go, but then you ask, why it goes this way and not it goes this way, right? You have heat here, you have cold here, it must go then, and then it creates big vortex. And then they notice that it always creates this way. Why? They try different things. And then they invited 25 graduate students, I mean, you really need a lot of graduate students to do this. They take their apparatus and they rotated it relative to the Earth's rotation. And then they notice that now it rotates in the opposite. It's Günther Ehler's theory, right? That's what I said. Students always drive science, right? So it's really, you need to break symmetry a little bit. I mean, just imagine, I mean, this speed of this vortex and the Earth's rotation, which takes 12 hours, right? Half period. And still it works. So you need to break symmetry a little bit, and then your vortex knows which way to go. Yes?
I have a question. Of course, that way the large-scale quantum flows can source energy from the
Small scale
3D turbulence. It's really important, maybe in supporting this large cyclonic flow. But have you done any calculation to find out is it important in the formation of this? The actual formation of large scale flows?
No, it's a very good question. No, it's, as a theoretician, I can tell you, it's a very difficult problem in the sense that I would like to, to look at the turbulence and to see if I put a little bit of a mean flow, how it would behave, whether it would grow or not. It's probably possible, and we're now trying to develop a formalism for it, because you need for this formalism of describing interaction between mean flow and turbulence. And in two-dimensional setting, this seems to be possible. And my PhD student, now Anna, she works on it, so we already have equations. They are pretty complicated, under some assumptions. If I a complicated integral differential equation, we're looking to solve them. But so far, no theory. Yes.
Если мы можем по-русски. Насколько сильно меняется при увеличении вихря его природа и характеристики, раз мы наблюдаем, что
ни в коем случае нельзя построить математическую модель или эксперимент на небольших играх, и при этом подобрать коэффициенты для того, чтобы предсказать по результатам для небольших игр результаты для больших. Okay, но насколько сильно меняется природа? Это зависимость нелинейная, она должна быть гораздо...
So that everyone understood the question, or you want me to translate it into English? So the question was, if we really can model and understand small vortices, why we cannot then rescale it into big vortices? In a sense, it's what is described by Reynolds number. Reynolds number tells you how many effective degrees of freedom you have in your system, right? So the smallest scale is where viscosity kills all the motion. So it's really when you have a relatively slow motion on a small scale, you have 1,000, 5,000, 10,000 degrees of freedom that we can model. The moment you go into any cloud which has 1 kilometer, for example, size, and the wind which is 20 meters per second, you have 10 to 6, 10 to 7 degrees of freedom, which tells you that it's not rescalable. That something which has 10 to 4 degrees of freedom and something which has 10 to 7 degrees of freedom is very, very different. All the more we don't know how computational requirements scale with the Reynolds number. It's still very much subject of arguments. No questions?
Why those giants vortices stop eating energy after they passed their mark? No, like you show us in red. And what happened?
Nobody knows. I mean, that's a good question. Nobody knows what, hurricane is an incredible complicated physical phenomenon. What happens at the height of 150 meters so that you stop getting energy of your rotation into turbulence, but you start getting energy of your turbulence into rotation? My guess is that as you go higher, the intensity of this motion is getting higher, and it's better suppress vertical components of turbulence. Because turbulence has this component and that component, right? That component want to give energy to the big vortex. This component want to burn energy into the small scales. And there is competition between them. This only qualitative understanding. Wait a second, there is somebody behind and then if you...
You started from the sun that it gives energy. The sun is the source of energy. I more like the, let's say, formulation or Gross formulation. The sun is the source of low energy. And in this case, applicable to your case, so the sun is the source of temperature gradient, not energy. And the question, in this sense, what is actually the situation? Let's say if we increase the sun twice in size, what parameters? Is it scales to any parameters of your model or not?
It's a good question, and particularly it's relevant to, for example, this discussion on global warming, because after all, you have a gradient between pole and equator, right? It's just temperature difference, right? Now imagine that you make your sun hotter, or you make your humans more active, and you increase the temperature of the Earth. What happens to this gradient? It will be more or less the same, because it's just given by the geometry. But a relative gradient, namely the temperature difference between pole and equator, divided by the mean temperature, will be less. And it is this relative gradient of temperature which drives this large-scale flow. And it is a subject of a very hot debate, what actually would happen as we experience this warming, whether we will see more hurricanes, more very violent events, or it will be less of it. And as a theoretician, my guess would be that because the relative gradient is getting less, we would see less violent events, we would see more stable weather patterns. And of course it would be politically incorrect to say it, but then other people went and studied what is called paleoclimatic records. Namely, you go to Greenland, you drill the ice, and out of the ice you can know what was the weather, namely the changes of temperature and precipitation in this part months after months, some 50,000 years ago, 100,000 years ago, and 1 million years ago. You can drill your ice that far. And it seems that this supports my idea, namely our idea, that the more warm years see less variability on the scales of tens of years. You cannot really distinguish in more, sometimes you can, but on a long time scale it's usually the accuracy. So in a sense I believe that it's really this relative gradient somehow influences the intensity of turbulence on your planet. But it's still a very much controversial subject. Yes?
Can I ask a low-level question?
Low-level questions are allowed to ask. Only professors are allowed to ask low-level questions. Huh?
Yeah. So okay, good. So in these plots, and also in the previous ones, when the x-axis is length scale.
Yes.
If you switch from length scale to time scale, will it move qualitatively the same?
Yes. Yeah, it's more or less, you have a plane which flowing through it, so you can, it takes, for this big, Boeing which flew from Chicago to Honolulu, it was easier. Now it's more complicated to do space-time transform because it's not a frozen picture of a wing. So you just don't do x minus ut transformation, but you can do it. Yeah, you can do it in frequency domain.
And you see the difference between direct and inverse cascades the same way.
Yeah.
And you know the power loss.
Well, in this big scale, it's just easy translatable, namely r scales like t, because the coefficient between them is the speed of your aircraft.
No, if you do it stationary.
If you measure stationary after some time, it's called Taylor-Frozen hypothesis again. If you assume that there is a large-scale flow which drives turbulence through your probe, and you just measure in different times. But its data are much messier, usually, much more messy. But the scaling is kind of...
The reason I ask is that in condensed matter systems, people are much better at measuring time than space.
Yes, it's actually Landau, during a war in 1942, when they were in Kazan and they heard the talk of Kolmogorov, the Landau retranslated it immediately into a different time measurement from different point space measurement. That's what Landau did. Of course, he never published it until in 1944 he finished fluid mechanics. Because you know what he did during the war? He was calculating, explosives and jets and all this. Yeah. So he learned fluid mechanics. By this time, wrote fluid mechanics in 1944, and there he put his, without contribution to himself, this statement about different time measurements. So it exists. But usually experimental is kind of messy, but it's doable. Yes?
We could get some kind of explanation for this boundary layer between the surface of the sea and the level where your cascade change its sign.
They already asked. No, I have a starting idea is that the intensity of the hurricane is higher up there, and because intensity of this, then it's better in providing its low energy supply. Right? But it's a hypothesis.
My question was, haven't you seen anything like that on the boundary layer in your small-scale experiment?
That would, no, we just cannot resolve it that good, because it's a 3 millimeter layer in which we already measure. I mean, we did measure the vertical profile, which is over here. That's millimeters, and this is a relatively thick layer, which was a 10 millimeter size, and then we can really measure a profile, and you can see that near the bottom, the vertical component is not suppressed, and as you go away from the bottom, it's more suppressed. So it supports this picture, and remember, the same guy who did this experiment is the same guy who analyzes this data, so he knew what to look for. But so qualitatively it looks like it's similar, but it's only for this thick layer we can distinguish it. When we make it thin, it's already our resolution is not good. Yes?
In complete, I have a question about computer simulations. Did they simulate the trajectory of every particle by means of
it's
somehow in another way?
Yeah, it's a very painful way to simulate trajectory of every particle, but for this simulation in which you do with the real boundary conditions, the real physics, that's what you do, and that's what it makes so slow. Usually, numerical people prefer to have a periodic boundary condition, assuming that you do your experiment on a torus, like everything is periodic, and then you use spectral method, which is much faster. But if you have a real box and you want to calculate flow of a real box, if you have a turbine and you want to calculate flow of a turbine, then you solve it in a real space, and that's great. Yes?
Well, I have actually two questions. You said that the energy generator for the Earth is the sun, yeah? And it creates big vortices on the whole planet.
Yes.
In this work, you were considering like inverse energy cascade. But to predict weather on the scales of 100 kilometers, aren't we supposed to go from direct energy cascade? So from large scale vortices to small ones?
That's precisely the point. First of all, sun also produces this convection. It's also produced by sun, because it hits the ground and then it creates a vertical gradient. So sun produces both large-scale flows and small-scale flows on a tropospheric scale. Now, what we do know that the big, large-scale flows don't give energy to smaller scales. Two-dimensional flows don't produce fragmentation and the energy transfer towards small scales. That's precisely the point why we need to explain how this 100 kilometers vortices can get their energy from smaller scales. And partially it explains. Second question.
On the Earth, smaller scale vortices, one car goes that way and the other car goes the other way. Why the vortices doesn't compensate each other?
Why they all don't die out and we enjoy the permanent summer? But first of all, inverse cascade, it in a sense, when vortices do compensate each other. Just imagine two such vortices which have like this, and in between they do compensate. This tries to create this jet, this tries to create that jet. As a result, it does not move, and you create one big vortex. That's the mechanism by which planar vortices create larger and larger vortices, right? And also you always, but we produce, I mean, it's much messier. I try to give you a very oversimplified picture. I mean, on a real situation, you have ocean, you have land, you have different scales. You have albedo changing on all scales and producing winds of different. This is a very messy system. This is a very oversimplified picture. Yes. Time is over, I'm told, and some people want to eat.
No.
The idea is that another announcement.
Can you say what you said again about programs Weizmann?
Yes. So people want to stop me asking questions and advertise what I advertised last time, namely that particularly for undergraduates here, but also for graduates, there is the Weizmann Institute of Science, which Ulf Leonard and me, the first lecture and the third lecture today, which we are from this institute. If you want permanent summer, it's a place where you want to be. And in particular, I want to advertise a summer program for undergraduate students, and it has a November 1 as a deadline for application, and it's very easy to apply online. It's very difficult to be accepted there. It's a very elite program to which we accept only a few people, but it's something which is unbelievably good, trust me. And it's usually every student gets paid a stipend, put into the lab or theoretical group and does real research for 2 months, and then they meet each other, they go around the country, they have beautiful time, and all this. So here are the formal data, and here are the, I actually translated it into dollars because not everyone knows how much shekels, so that's the stipend you get, and then the details. And so I very much encourage you to apply. There are not many such programs in the world. There are in Levitovstok. You put now your computer advertisement for us. There are particular programs for girls, which I encourage girls to look for, women in science program, etc. There are several of them, and some of them are really very much targeted for girls. And Try to widen your horizons. Go away, go abroad, spend some time, see people. In particular, this program will most likely this year will have some special quote for Eastern Europe, and I very much advise you to try to fulfill this. Right? Okay. Thank you very much again. And now,
Thank you.
Now learning changes the things. I want to give these prizes, and they are still unsigned, but I'll give it to you, and then if you want, I will sign it to you, and this two of you, and for the best wishes. I have one version in English and one version in Russian, and it's English version is Cambridge, and this is Russian, but Russian is better. First of all, I like better in Russian, and then it's you can see here later that I put a lot of remarks that people did. So, you want any preferences, or you can randomly choose? You have any preferences for language? No. Good. So you choose left to right. Right. And you want to start also for yesterday, right? So, okay. Remote is over there. Upstairs.
Yeah, so listen, I'm sorry for eating into your lunchtime, but some people came and asked about what we discussed yesterday, and I wanted to maybe do a quick summary for those who came today and were not here yesterday, and also maybe someone was interested to hear more about it. So basically there were two messages. There was a message for adults, and there was a message for students. So this was, page one was message to adults, trying to explain, how the system in a research university works. There are students studying and also researching on campus, and it's integrated, and all students have the possibility to do research as undergrads in the labs, and they're encouraged to do it, and there is a system that organizes them. And in the system, the toy research that students do, it gradually morphs into real research, and students can get quick calibration of themselves and see whether a particular area fits or doesn't fit. And so for example, at MIT, whatever a student wants to do, he can go anywhere and do research. So space engineering student can go do 2 months research in biology, 2 months research in chemistry, two months research in physics, and then at the end, well, that's my my former advisee at the end start doing string theory, which he's doing now, and so on and so forth. And so very very nice to have such a system, and that's how. How it works, and we are not the only ones who have that. There are other universities who have that type of system, and we have partnership with them, and we have students exchange over over summer, etc. And it works very nicely. Also part of that is exchange of master students. We don't have master students, but we can handle master students of other universities as Europe students. Right, and then so that was for adults. If you want to think about future and how systems should evolve towards Western. One of the successful models would be this one. Then there was part for students, saying that if you don't care about changing the big system, what you can try to do is just probe yourself using some programs that exist for that try to provide to students the environment like what